Welcome to day 2 of PyaR 2024A. I hope you learned something yesterday, and I hope you're ready to learn more today. We'll pick up from where we left off yesterday, notebook 3. But before we go there, we will cover a little bit of astronomy, a little bit astrophysics background that will help you make sense of things. That you'll see in the following notebooks from notebook 3 to notebook 6. And as always, remember to post your questions on the Slack. The mentors are here to answer your questions. Please give the mentors a little bit of time to get your questions. There's no need to cross-post them to the Zoom chat. You'll see some resources in the Slack channel. In the Slack channel, there's some helpful links. There are some Q&A. There are some people ran into some problems, and we helped them out. So maybe you'll find something useful. Maybe you ran into the same problems. Okay. Before I begin with the astronomy section, does anybody have any burning questions from yesterday's session? Please feel free to unmute yourself and ask. And don't worry about notebook 3 if you are still unclear on some things in notebook 3 about astronomy. It will make sense. It will make sense after this astronomy background section. Okay, I don't think there are any questions, so I will begin. I will share my screen. Oh, what's my quote? Yeah, fine. Okay. Great. So let's start by looking at some properties of stars, how we study them, how we measure them, and what we can learn from them. So stars, what properties can we measure about a star? Give me some guesses. Feel free to put your guess in the Zoom chat. No need to go to the Slack with this. What are the properties of a star? A very distant star. What can we measure, or what can we, conceptualize? Anything, any guesses? When you think of a star, what physical properties do you think of? Brightness, yes, that's one. What else? Color, right. Distance from the Earth, size, yes. Color. Okay, we have a few. Great. I hope we are in full screen now. Okay, so what can we measure about a star? We can measure how hot it is. Okay. Of course, we can't do this directly. We can't take a thermometer to a star and point it at the star, or dip it into the star. So we have to measure that indirectly. We can think of how far away it is from the Earth, as somebody pointed out. We can think of how big it is, right? We can measure how big it is, again, indirectly. We don't have a tape measure to wrap around any star. Like somebody pointed out, yeah, that's size. And how bright it is, right? Brightness was the first guess in chat. And of course, what color it is. So color is a tricky term in astronomy, as we'll learn. But these are basically the properties that we deal with. So how hot it is, the physical quantity that gives us information of how hot a star is its temperature. and it's measured in kelvins. How far away it is usually measured in parsecs. Astronomers don't usually use light years except for like science communication. How big it is measured in meters, and the mass, or how heavy it is, that's also a measure of how big it is measured in kilograms or solar masses. So how many suns worth of mass a star is. That's a measure of mass. A solar mass is a measure of mass in astronomy. How bright it is given by something called a magnitude. Okay, and we'll see how we can measure magnitude and how much energy it gives off in total in all kinds of radiation. Okay, is given by the luminosity. Defines the luminosity. But luminosity is a little bit difficult to measure. The magnitude, as we'll see. And finally, what color it is defined by the color of the star, which is an astrophysical quantity measured using the magnitude. So, magnitude. Magnitude is measured in a weird scale where negative numbers indicate that a star is brighter. And basically, this comes from the ancient Greeks, who first started cataloging these stars. And they came up with this very nifty system, which is that they found the brightest star in the sky, and they called it magnitude 0. Okay, they call the magnitude 0. They call the brightness 0. And that way, when they found fainter and fainter stars, right? Like say traveling to darker sky regions away from whatever city they were living in. They didn't have a lot of light pollution then, but still, that gives you the opportunity to define fainter and fainter objects with bigger and bigger numbers. Whereas if you were to define 0 as the faintest object in the night sky instead of the brightest object, whenever you found an object fainter than that, it would turn out to be a negative magnitude. Okay, and they didn't want that mess. But when we adopted the system, and when we redefined how magnitude is measured, we started using negative numbers. So negative numbers are allowed now, and it feels a little bit unintuitive, but just remember that negative numbers are bright when we are measuring magnitude of an astronomical object. Now, there's two kinds of magnitude, apparent magnitude and absolute magnitude. Okay, so how bright a star is doesn't just depend on how much energy it gives off or its luminosity. It also depends on how far away it is, right? A very bright star, if it's very far away, will look faint, right? So that's the apparent magnitude. It's the one we directly measure from the Earth or from a space telescope in orbit around the Earth, right? And then we have absolute magnitude. Once we know the distance to that star, we can calculate actually how bright it is from a specific distance, from a fixed distance. And that fixed distance has been, is agreed upon to be 10 parsecs in astronomy. That's the standard. Okay, so absolute magnitude is given as the magnitude of the star as it would be measured from 10 parsecs away. Again, a parsec is a measure of distance, not a measure of speed or time or whatever Star Wars came up with. Okay, now, how do we measure magnitude, right? Magnitude is measured using something called filters. Filters are, you can think of them as basically glass, but colored glass, okay? But they're made very precisely, and they don't need to be glass. They can be other transparent medium, and they are very carefully designed to let in light in a certain wavelength range, all right? And the response of the filter will not be uniform across that entire range. You can see that this image, this plot, shows a bunch of common filters from a certain experiment, from a certain observing project. And you can see that the different filters UBVRI, which is a very common naming scheme, UBVRI or UBGRI, it's a common naming scheme. You can see that they all have different wavelength ranges they cover, and the y-axis gives you how sensitive it is in at any given wavelength, right? So the first one, for example, stretches from say 3000 to 4001. And you can see that it peaks somewhere around 4006 or 7. And then it tapers off, the response tapers off on either end. So we basically use one of these filters. We put one of these filters on our telescope, or like we collect the light and we pass it through the filter with the large telescopes. And we just measure how bright the stars appear in these photographs. And this process is known as photometry, right? And once we have the brightness of the star, the magnitude of the star, in two different filters, we can subtract these two values. Okay, we can subtract these two values to get what astronomers call color. Okay, and smaller values of this color indicate that the star is bluer, and bigger values of this color indicate that the star is red in color. Okay, so and usually this is usually we just pick one of the any two of these filters, any two of these magnitudes in two different filters. And you can see that a real life example here from the Sloan DSS survey from the SDSS. And you can see that the SDSS uses these 5 filters, U, G, R, I, and Z. And you can see that in the panel below, there are 3 real life stars, 3 real stars with complete spectra. These are called astronomical spectra. So when you take a spectra, you basically pass the whole light of the star, everything that you can measure with your telescope, through something like a prism or a special kind of thing called a grating. And it basically splits the light into a rainbow, which we call the spectrum. Okay, and you basically get to know exactly how the intensity, how the luminosity of the star is distributed across wavelength. And you can see that Vega is bluer, right? The blue line the star with the blue line tends to put out more blue light. So it will give you more, it will register more in the U and G bands, not so much on the R, I, and Z. The Sun, on the other hand, which is a very, very average star, a very typical star, will fall somewhat right around the middle. It will put out light in all the bands, but mostly in G and R. And finally, this last object to the right will put out mostly red light and will mostly register on I and Z filters and not the others. So that's how you can actually get spectral information from color. It's not exactly the same, but it's a very reasonable substitute, because taking spectra is far more complicated. Spectrographs are more expensive than simply doing photometry. you can do a lot of photometry very, very quickly. So we often use color as a substitute for temperature. So this again gives you a bunch of filters, but this time is for the Hubble Space Telescope, which is like the oldest space telescope, and it's still active. It's been active for decades. They launched it like even before I was born. It's been there forever. It's given us very, very pretty pictures of the universe. It's given us amazing spectra. And it's also given us a lot of photometry. It's given us the magnitude of different stars and different wavelength bands, which we used to measure the colors and which we will use to measure the colors with Notebook 3. So mostly we'll be using these two filters, I think, or maybe not, probably these two, yeah. And you'll see that we'll just we'll subtract the magnitude in these two filters to get a color. So what do we do with the color, and what exactly are we substituting? Why do we need the color information? So stars, based on the temperature and luminosity, so which is, you know, how much energy they're giving off, and the surface temperature, okay? Based on these two properties, primarily these two properties, they can be classified into a bunch of different classes, all right? And the best way to visualize that is with something called an HR diagram or Hertzsprung-Russell diagram, okay? Hertzsprung and Russell were two scientists, and they basically proposed this diagram. And you can see that there's a lot of information on this image. The x-axis gives you the surface temperature in kelvins, and the y-axis gives you the luminosity, which is, you know, the total energy that is putting out, the total energy the star that is putting out, not just in a fixed filter, not just in a fixed wavelength range, but in total, okay? And you can see that if we take a bunch of stars, we collect this information from a bunch of stars, and we all plot it on this diagram, you'll see these groups emerge, okay? There will be a streak here. There will be a uniform streak of stars, a uniform band of stars here that stretches at a diagonal all the way from the top left to the bottom right. And this is called the main sequence, okay? And most stars, not most stars, but all stars go through the sequence. All stars spend most of their lifetime in this part of the Hertzsprung-Russell diagram. And this Hertzsprung-Russell diagram basically shows you the evolution of the star. This shows you the life cycle of the star. Okay, when the star eventually dies, it will go through one of these phases, which are the giants and the supergiants. We'll split the giants into two groups again in subsequent slides. And then it finally settles in this area, which is called a white dwarf. Okay. So you can see that the luminosity here is measured in solar units. So if we target 1 solar luminosity, you'll find the sun somewhere around there. And here it is, here's the sun. So the sun would lie somewhere around here on an HR diagram. And its surface temperature is just over 6,000 kelvins. And you can see that there's a bunch of other things here, a bunch of letters. These give you something called a spectral class of the star, which is really a more nuanced way of classifying stars. And for our project, for our tutorial, Hubble only observed stars that are brighter than the sun. So we'll mostly be looking at stars that come from this top half of the diagram, top half of the HR diagram. Another thing that we'll notice is that this diagram is colored, and unlike the color scheme that's used in most other things, blue here actually means hotter, okay? If you look at the x-axis, you'll see that temperature increases to the left, okay? Temperature increases to the left, And if you look at the y-axis, you'll see that it's a logarithmic graph. Okay, it's a logarithmic axis, right? So it's not going 1, 2, 3, 4, 5. It's going 1, 10 to the power 1, 10 to the power 2, 10 to the power 3, and so on. Okay, because luminosity is measured in a logarithmic way. So as you can see, for stars, blue stars are actually hotter. Okay, they're hotter, they're bigger, they have more mass, and they actually burn out pretty quickly. So they live much shorter lifespans. They live for they don't live as long as the stars that are redder and smaller. They have more fuel, but they also burn it more quickly. Smaller stars, on the other hand, don't have as much fuel, but they burn it very slowly. It's a slow burn, it's sustainable, and they spend much more time in the main sequence. So that's the HR diagram. A lot of information here. But again, like we discussed, luminosity is kind of difficult to measure. It's kind of difficult to take the spectrum of a star to measure exactly how much energy it's putting out in total in all wavelengths combined, and to estimate the surface temperature using the spectrum. So what can we do? How can we make our job easier? Let's see, but first, once again, let's focus on the main regions of the HR diagram. Of course, we have the main sequence, and we have the giant branch, okay? And the giant branch here has a horizontal branch, and this is where red giants lie, something called red giants, okay? We will encounter them in the following notebooks. And we also have something called an asymptotic giant branch, which is everything, all of the giants that lie above this red giant branch, okay? So remember this diagram, remember these three groups, remember everything above this H-core exhaustion period, okay? We're measuring bright stars for our project. Let's see if this pattern emerges in one of our notebooks, in one of our tutorials. So let's see if we can find this pattern of the main sequence being an offshoot to the left, and the RGB and AGB being two diffuse groups to the right of the diagram, AGB being above the RGB. And to do that, we will simplify our work. We will not be making an HR diagram. Instead, we'll be making something called a color magnitude diagram. So I discussed how luminosity is difficult to measure and how magnitude is a reasonable how magnitude is a reasonable substitute for luminosity, and how color, astronomical color, is a reasonable substitute for the temperature. Yes, somebody was saying something. No? Okay. Anyway, so we create something called a color magnitude diagram, where we plot the color on the x-axis and the magnitude on the y-axis. And you will see, once again, negative magnitude indicates brighter stars. They indicate more luminous stars. That's why the y-axis decreases from the bottom to the top. And the magnitude, once again, is a substitute for temperature. So, sorry, the color is a substitute for temperature. And hottest stars lie to the left, and coldest stars lie to the right in the color magnitude diagram. This is actual data from a project plotted on a color magnitude diagram. I will stop the slide sharing, and I will share a couple of other things. So here you can see sorry. Yeah, here we can see much better, much more detailed magnitude color diagram from Gaia data. Gaia is an amazing satellite, an amazing space telescope. It's given us a lot of data, and you can see that there's so many stars. There's what 4 million stars in this image. So much so that the scatter had to transition to a heat map here. And as you can see, real world observations. If you plot real world stars onto a color magnitude diagram, you will get a pattern that's very similar to an HR diagram. Once again, remember this pattern with the splits, the main sequence to the left and the giants to the right. See if it emerges in one of the following notebooks. Finally, I'll quickly go over something called Doppler shift. So Doppler shift, you're all familiar with this phenomenon, believe it or not, but you have not seen this with light, except you've observed this, you've heard this with sound. So, what is Doppler shift? Let's see. Let's start the slideshow. The Doppler effect, you will be familiar with the sound of an ambulance siren or a police siren, usually, if you're American, I guess, or a train whistle. You will see that when the ambulance is stationary with respect to you, when it's not moving, there is no change in the pitch of the siren, okay? Not just the loudness, I'm not talking about the loudness, but the pitch, okay? There's no change in pitch. But if the ambulance is moving, if it's passing by you, if it's approaching you, okay? When it's approaching you, you will notice that not only does it get louder and louder, it will also get higher and higher pitched, okay? It will sound more and more shrill. And once it passes by you and it starts moving away from you, you will see that it sounds quieter and quieter. And also, you will see the opposite change in pitch, right? So it will sound less and less shrill. It will sound lower and lower pitch, okay? So that's the Doppler effect. Why does this happen? Well, you can see, you can model sound as waves, okay? And when the ambulance is approaching, these waves tend to get squished together, okay? And the wavelength decreases, which increases the pitch. And when the ambulance is moving away from you, the wavelength increases because the waves get stretched out and it sounds lower and lower pitch. The pitch decreases. And something very similar happens with light. As you can see, you can see with the sound waves, the sound wave fronts, you can see how they're squished together and how they are spread apart. And something very very similar happens with light waves. Light waves also get squished together. You can think of them as being squished together or being stretched apart. Okay, stretched out. And that depends on the velocity of the source. If the source is moving away from you, the light will get stretched out. And if the source is moving towards you, the light will get squished. Okay, so if it's moving towards you, the light will be blue shifted. Okay, so the lines that are supposed to appear in regular places. Okay, the signs that okay, so you get some of these lines. Okay, in the stars, as we noticed in the previous slides and the other slides, that the spectra are not smooth, right? The spectra are jagged. The spectra have something called absorption lines. So there are sudden dips in the spectrum. Okay, and those dips are called absorption lines. And these absorption lines, depending on the composition of the star, always show up at exactly the same wavelengths. Okay, they're supposed to show up at exactly the same wavelengths, as long as the star is stationary with respect to us, okay, in terms of radial velocity. So this is light emitted when the star is at rest with us, and this is light emitted when the star is moving with respect to us, okay? The star is moving away from us, so it's redshifted, and you can see that all the lines are moving to the right, okay? It's moving to redder and red wavelengths, or the absorption lines are moving to the redder and redder wavelengths. So why don't we see this? Why don't we see the Doppler effect with light in our daily life? Well, because the change is very, very tiny, and it doesn't happen when the velocity is very small. Velocity of the source is very small, which it is in terms of things that are on Earth. You need very, very high velocities of the source to see this effect. Which is only usually observed in space, in outer space. You can see, once again, there's a real-life example. And you will encounter this formula, this nifty little formula for the redshift in Notebook 4 that Philip will take you through. But for now, I will stop sharing and pass it over to Lodrick. I'm sorry, I almost took 30 minutes, I think. Lodrick, please take your time. You don't have to rush it. I hope I have helped you with the background, by providing the background. If anybody has any questions, please put them in the Slack channel and we will respond. Okay, let me stop sharing.
I think, yeah, you've made my job much easier. And
God, I forgot how to stop screen sharing.
oh, no.
Can I leave the host help me, please? Or Lodrick, you can just share your screen. I think it overrides it.
That's true. That'll work as well.
Yeah.
Okay.
Oh, here's the stop button. Yeah. It blended in with the spectrum.
Oh,
I have a quick question, Aparajito. Can I share the presentation slides, a link to the presentation slides in the chat with everyone?
Yeah, absolutely. And also in the Slack channel. I will put them in the Slack channel. You can copy them over. Yes.
Great. Thank you. I'll put them in the Zoom link, in the Zoom chat here.
Yes.
okay. Oh, dear. Okay. For a moment there, I lost the window that I wanted to share. Is what I'm sharing correct? I'm not sure. What do you guys see?
Yeah, this is Notebook 3. Yeah, this should be good.
This should be it, but okay, I'm sharing it on VS Code, but I wanted actually to share it on
Well, as long as we can make the plots, I don't think it should be a problem.
Oh, okay. Let me just share it on Firefox.
Yeah.
Okay. Thank you very much for that again. I'm gonna quickly go through this. There was a part that was not super clear yesterday. I'm gonna try and explain that more. So here we're importing the things we need for this library. Here we're setting up the fonts and how we want our plot to look like, and we got a preview of that yesterday. And then there was this function. This function is a little bit not very intuitive, mainly because these things were not defined explicitly here, but yeah, but it's quite simple to understand. And I think, is it okay to talk about docstrings a little bit? Aparajito? Should I mention docstrings?
Sorry, should he mention what?
Docstrings.
Should he mention what?
Docstrings.
Yeah, sure.
Yeah.
And really quickly, Lodrick, can you please zoom in so we can see the screen better?
Oh, okay.
Thank you.
try and zoom in. Okay. Is that better?
Yeah, this is good.
Okay,
Thank-
great. Yes, so basically doc strings are things we write on our functions so that when we come to them a few days, months later, we remember what they were doing. And so usually we put something like this in the beginning of a comment, and this is a good habit. It's not a must, but it's a good habit to have. And so you would write that this function, what does it do? It makes text files of catalogs. And you would say something about the parameters. And for the for example, the first parameter is catalog name. You would say something like, this will be the name of the file. And usually we write some notation here to show what kind of file it is or what kind of parameter you're adding. So this is a string. So we just write str for string. And so
by the way, sorry, by the way, everyone, this is this 3 quotation mark thing is basically just a multi-line comment. You've seen comments before with Notebook 1. Comments are a way to communicate with other users and not the computer. So, you know, just like the single line comments that we use, we put there with the hash symbol. Multi-line comments will also be ignored by the computer, but it's a way to communicate with your fellow users. And putting a multi-line comment in this exact position when you're defining a function, when you're defining a user-defined function, lets you access this comment through the help command. And it's a really, really nifty way to, you know, help out yourself a few months down the line, or somebody else who is not familiar with it. Yeah, Lord, go ahead.
yes, so as you can see here, here I'm basically defining exactly what this function does. And let me just finish this line. And the name of each parameter. So for example, catalog name is just a string, which will be the name of the file, okay? Params is a list, and it's a list with sublists. So basically it's gonna be a list that contain everything. I'm gonna show a very quick example in a few seconds. And then param name string is just a string with the name of the params and this param name string is the thing that goes on the first line. So to see that, I talked about a little bit about this yesterday. We have a line here that says catalog. Catalog is just a variable. Open a file with the name catalog name, as I said here, just the name of the file. And then catalog.write, we write a hash just to, this is the way we comment out lines in our files. And then we write param name string, okay? This will go on the first line and basically shows what parameters are in this file. And then there's /n, which means next line, okay? So before I begin, let me show you an example here very quickly. So I made this yesterday, and I said, let me name a string. So here I said name string, I said name, height, age. Means my file will have a name, a height, and age, okay? This is the value that I'm gonna enter for param name string, okay? And
by the way, Lodrick, I think we can skip over some of these, some of this minutiae, because you know, we are in a bit of a rush.
I'll get to
but
it.
yeah, to just you know, summarize what the functions are doing, and I think the learners have enough background to, you know, just go over the individual lines of code on their own, and we encourage that they go over them on their own. Just remember to define what the different properties are in the catalog. That's
Okay.
it. Yeah.
Yeah, let me just go through this very quickly. So here I just put some names, and then I put their ages, and then I put their heights. And then I did make a file using this this command. I did make a file yesterday, and I'm gonna show you that file now. here's the file. So as you can see, that first line that I was talking about is here, name, height, age, and then the names, and then their height and age. Oh, I think this is a little bit backwards. But yes, I think you get the idea. So I'm gonna continue with the actual code. Let me just remove this. Is this still running? Yes, great. So we're gonna use this function later, and basically we're gonna use to make the file like the file I just showed you. Okay, so let's move on to this line. So in this function, we are making the file, but this is just another way to open a similar file like the one that we just made. And so we use the NumPy function load text. And I think I showed this file yesterday. So when you have a text file like this, as you can see here, okay, I'm gonna talk about the path very, very soon. That file is over here. This is htst.data.txt. This file was created in a similar way that I created that other file that I just showed, this file. But you can see it has more parameters here, okay? And this file has parameters basically about different stars. Every line you see here is talking about a different star. And it has the array, which is just coordinates in the sky, longitude you can think of, and then we have dec, which is the latitude. We have psi, which is basically just the distance from the center of the Andromeda galaxy. I'm sorry, I forget what ETA was. What was ETA again?
ETA is eta. That's another way of Chian eta. Another way is another way of measuring the coordinates. I think that's with respect to the center of the Andromeda galaxy.
Oh, okay.
Yeah, probably.
With respect to the center of the Andromeda galaxy again. And then this is one of the magnitude measured with a filter that had a wavelength of 475 microns. And then it's another magnitude measured with another filter. And then this is the velocity of the star in kilometers per second, and this is the error in that velocity. We are not going to be using these two columns in this particular notebook, but we will be looking at this. Okay, so basically this command here, it goes to this file. So as you can see here, where we are right now, these two dots, they simply mean go back to a directory it's just the same way you would go back as in if you were, let me open something. Oh, there is no directories. Oh, okay, here. Okay, so for example, you are in plots, and then you want to go back from plots to blank notebook. So the way we denote this in code, we just write, even if you don't remember the name of the directory, you just write two dots. And this is something we call a relative path. So if you write two dots, means go to the previous directory and then find a directory named data. We just separate a directory with backslashes. Find a directory named data, and then in that directory, find the file named tech.data.txt. I'll show you how exactly that goes here. So this notebook number 3 is over here. When we write the two dots, so we are here, okay? Let me go back. We are here. We write the two dots, it goes back. So from where we are here, it goes back to programs. Sorry, we're in programs. It goes back to blank notebooks. And then it finds a directory named data, is what this line here is saying. Find a directory named data, okay? So let's find that directory. The code goes in, and then you can see there's lots of files here. It opens the file named htst.data.txt. And that is basically what this line does here. So after finding this file, it opens it and just unpack this tree is just a way to tell it what kind of data you want to open. And then how do you open this file? You can see here we have specified a couple of different variables. So basically, the way this function works, it knows to assign each variable to the specific column. So as you remember this file here, array, so this array column, all the numbers in array here will be assigned to the variable, will be assigned to the variable array. And the next one, dec, will be assigned to the next column, which is dec, which is dec. I'm gonna close this now, because I don't need it anymore. Which is dec, and so forth and so on. So psi will be assigned to the directory psi, and eta, and all the others. And then after assigning all those things, I can show you very quickly. Maybe if I write print array. Let me first run this function. And then print array. You can see all the numbers here in array are now in this variable array. And so after assigning all those things, what we did was take the color, or make the variable named color, and take one of the filters, magnitudes, subtract to the other filters. And then I think yesterday I printed color here, just to show how that. So now we have this stored in this list. And so what's next? We basically just initialize the plot, which is basically talking about initializing this plot. And then after that, we write this line, plot, scatter. We are plotting color. So basically it's X, Y. So we are putting color on the X-axis, this color that we found here, after subtracting these two magnitudes, against one of those magnitudes. And this is the Y-axis. And now we're gonna plot them. This is just specifying the color, and this is just gonna specify the size of the dots on the plot. And the edge colors, we don't need those now. So let's plot and see what happens. You can see we have a very nice plot here. With every, so each point here, basically the x-axis represent what is the color index, and the y-axis represents the magnitude. I think I've covered a lot of stuff there. Is there any question? No? Great. Okay, I will keep going. So this is just one of the ways to plot. You use a scatter plot, means it's just gonna plot each point. And then I'm gonna move on to now a little bit of an exercise. Let me look at how much time we have. Or maybe everybody can go do this on their own. I'm thinking, do we do this exercise, or should I just
yeah, we need to do this exercise because they will be using the catalog files they create now to for the following notebook. So we need to go over this one. Do you have the complete notebooks, Roderick?
I do.
You can just copy the code from there and rush through it. No problem.
Oh, sorry, I just copied the code and just show everybody how it runs?
Yeah, and you can just explain how the parabolas separate the different regions, and that's it.
Okay.
Yeah.
So here I'm gonna plot again. And talk about that plot a little bit. And so before I talk about that plot, you can see here I defined something like we call a condition. You saw yesterday when Doug was creating ages and then selecting a different age. So the main sequence stars, we identify them by if they have a color index less than 1.75 and they are brighter than 23. So as you remember, when it's brighter means the number is lower. And so we look at this curve here. Oh, it's not inverted. I was expecting it to be inverted.
If you just look at the image, like if you look at the plot, everyone, before it's even colored, you will see that there's 3 distinct regions in the plot. The ones that's highlighted now in blue, the big chunk of gray to the right, to the bottom right, and the more sparse scattering of points above that, above the group of, above the cluster of points to the right. Yeah, so those are the 3 regions that we are trying to mark. And yeah, Back to you, Lodrick.
Thank you. Yeah, thank you. I had forgotten to mention that. So one of the aims of this notebook is just to try and mark these regions. Let's look at them here. So yeah, here is the first region, which I just marked in blue. Okay. And the other task is to basically select this region that is clustered over here. And as he said, the other task is to select these stars. And so we're going to look at how can we select those. So as I just mentioned, one of the ways is just to select everything that is has a color index of less than 1.75. So you can see roughly this line over here, and everything to the left of it we will have selected those particular stars. And then trying to select these stars is going to be a little bit more tricky. So we are only left with two groups. We have to somehow select these stars and then these stars. And these stars are going to be the blue giants. Is it the blue giants?
The red giants, onto the bottom are the red giants. Yeah. Yes. You can just use the RGB label. Yeah.
Yeah. Oh, nice. Okay. Yes. They're gonna have the RGB label. So I'm just gonna call them by the initials, the RGB and the AGB. So how do we select this is what we're gonna try to do. So as you can see, we did that for the blue. Let's try and do that for the red. It's gonna be a little bit more tricky, but we're basically gonna look at this and think of it as a parabola. And then we're gonna plot a parabola. Let me copy that code. Sadly, I have that code in a different computer. But no worries, I can get it done.
Yeah, if you have any trouble, I can take over. And once again, to the learners, please don't cross-post your question to the Zoom chat and to the Slack channel. I have been repeating this. Please cooperate with us. Please be patient. Our hands are a bit full, as you can tell. We will respond to your question. And remember that the recordings will go out. And you will be able to watch them on your own time. You will be able to practice. And hopefully, some of the questions will be cleared up when you run them on your own, when you run the notebooks. Lodrick, do you need me to take over?
Just 1 second. I'm just copying the code from my other computer.
That's okay.
Yeah. Okay. Great. That is done. Let me just go into now. Okay. Yeah, here you go. Some of it is not really. There you go. This is not part of the code. Okay, as you can see here, yeah, also this now we have selected the main sequence stars. And also after selecting the main sequence stars, you can see we wrote a catalog file for those main sequence stars in the data directory as before. So before I run this, I'm just gonna show you the data directory now. As you can see, there is, oh, okay, the files already exist in there. Basically, we're gonna be writing these files. Okay, and the reason we are writing these files will only be selected that satisfy this particular condition. Okay, so that is why we use the write catalog function. So as you can see, the name of the file, it will find the path selected, and then they will have these names as the param name string. Okay, and then for the next part in selecting the RGB stars, you can see here we use a quadratic equation, which is similar to a times x minus h square, x minus h in brackets plus k. So here the x-axis is given by color, and h and k basically define the minimum point. And I think I have to plot this. It will be easier to show them once I've plotted it. Let me plot it. So here, basically, this is kind of the parabola that I was talking about. And here is the minimum. So you can see the minimum is around, what is this? X is around, yes, around 2.1. So this is the minimum of this parabola. And the y value is 20.4. You can see here, it's around 20.4. This is basically the minima of our parabola. And we have used that to create a parabolic line. And we have said that everything less than that. Where is the line? Okay. Yes, so everything everything fainter than that will basically be part of the RGB stars. And I am saying fainter than that because please notice that this
Lodrick, can you please zoom in a little? I think everybody has to, yeah, on the code, yeah, please zoom in a little. Pause for a moment for the RGB and the AGB sections, because everybody has to copy those two sections. If you scroll down a little to the AGB section, yeah, that's perfect. Yeah, that's perfect. Great. So once again, sorry, we can't show the diagram and the code at the same time, but please copy over the values of the A, H, and K. And you can see how we are marking two different regions using the same parabola, one below the parabola and one above. And the region below the parabola are the RGB stars, and the one and the stars above the parabola are the AGB stars. And that should, match up with what he observed for the HR diagram. The three regions, if you remember, that's roughly how they're placed in the HR diagram, above for stars that are hotter than the sun. Yeah. Everybody please copy over this code. And if you have any questions, I think you should ask them now so that Lodrick can answer. Before we move on to the next notebook with Philip. Please run these lines of code because you will need the catalog files for the next few notebooks. Yeah.
And yeah, I think this is the end of this notebook. Once you have selected this, oh, there's a little bit more, and you can calculate the function of the main sequence stars. Just take the total sum of the main sequence stars to the number of stars in total, and similar for the RGB stars and the AGB stars. And here you go. Here, this line is basically just saying selected is everything that is the main sequence star, or this line represents all in Python code, or RGB star or AGB star. That he put that in the groups he called it selected. And then here he's just taking the sum of everything that's not selected. This is a not sign. Everything that's not selected, the sum of that divided by the number of stars, you get everything that's not selected. It's this function here. And that's the end of this notebook. Thank you very much. Any questions?
Philip, are you online?
Shall I start sharing them?
Yeah.
That's the question that someone has. How do you ensure that there are no logical errors? Maybe Roderick, do you want to answer that?
How do I ensure there are no logical errors?
Well, this is a more specific programming related question, so I think we can go a little.
Well, I guess you can, I guess you have to look for any anomalies. For this case, we know what what this diagram is supposed to look like. We know that these three groups should exist on a color magnitude diagram. If they didn't, that would be a problem. Then we would know that there's some kind of error in the way we wrote the code. So yeah, this is basically not that important a part of the project. This is something that you do on your way to doing the real thing. And that's exactly why we are doing it at Notebook 3. We're doing it early on.
Yeah, because this step actually creates three subsets of the data that we will need in Notebooks 4, 5, and 6. Well, 4 and 6. Right, Aparajita, is that what you were asking?
Yes.
Okay.
Yes, I think that's what the question was. I think the question was basically, how do we make sure that we didn't make any mistakes in this entire workflow? And yeah, the simple answer is that we are looking at the plot, and the plot is looking like your regular HR diagram, your regular color magnitude diagram. Yeah.
Yeah, we know we've made a mistake if the red points were not confined to the lower right, for example, or the green points were not confined to the upper right, or the blue points were not confined to the left. The plot itself is vindication that of the code.
The guy asks, what are the challenges associated with integrating CMTs? But there aren't any major challenges, I guess. It's a pretty simple process.
So Aparajita and Roderick, I'm seeing something here. I'm seeing red points in the upper right, and we shouldn't be.
Yes, so I did that on purpose to show that if something wrong happens, you can
Exactly.
see, yeah,
Yes.
this is not right.
Good, got you. Thank you. Thank you.
Hmm.
That makes a lot of sense, Roderick. Thanks.
And now it looks correct.
That looks just like it should.
Yes.
Great. If there are no more questions, should I start?
Yeah, I think Philip should begin with Notebook 4.
Can everyone see my screen now? Sorry, were you able to hear me?
Yes.
Yeah, we can see your screen and we can hear you.
Okay, so I'm just going to just talk a little bit about the Doppler effect. Already Apache has covered most of this. I'm just going to put a small connection to the notebook. So I just, so as Aprajita explained, when we look at a star and we look at the light that we get from the star, we see a range of different colors. And we also see sometimes certain features in the star, and these features are related to the elements present in the star. And they often come out as small dark bands. So here's a little caricature of what it might look like. But as we noticed from the description above, that that when an object that's emitting light and other waves is either moving towards us or moving away from us, the actual frequencies or wavelengths that we get from this object are in fact changed. And the reason, as Aprajita explained, that we don't see something very cute like this, that a little car coming towards us is sort of more blue and a car moving away from us is more red, is because the quantity of interest is the speed of the object relative to the speed of light. For sound, it's the speed of the object relative to the speed of sound. But for light, it's relative to the speed of light. And everybody knows that the speed of light is an extremely large number. And therefore, we don't actually see something like this in day-to-day life, except when we look at objects like interstellar objects, say stars and so on, because they do in fact move at very, very high speeds relative to us. So if we're able to take the light from a star and look at it very carefully, we would be able to see a slight shift. So for example, I'm showing two spectra here. One which is of a star that is, say, at rest with respect to us, and the other is of a star that's moving with respect to us. And what you should be able to see is that the same types of lines exist in both of these spectra, but they are shifted towards the right. So in this particular case, you should be able to see that they're shifted a little to the right towards the red region of the spectrum. And so this star is red shifted. Its light is red shifted, which means that it's moving away from us. And there's a little formula which we'll be using in the notebook below, which is that when you have a wavelength that is emitted by a star that is at rest with respect to us, when we receive the wavelength, if we're moving with respect to the star, we would get the wavelength shifted by a number 1 plus the speed divided by c, where in this case, we're taking a positive v to be the star moving away from us. And that you should be able to see that this means that if you had a certain wavelength, this entire number would be a positive number. And so the new wavelength would be greater than the rest wavelength. In other words, you'd get redder light. Of course, we don't often see caricatures like these little rainbows. What we actually do collect is something that looks more like this curve that's here at the bottom left, which is a sort of intensity of the rainbow as a function of different wavelengths. And you see that there are these clear features, these lines over there, which sort of translate into little dips because they're darker lines. And so if we looked at a star, say the sun, for example, we might see such dips, and they're well-known dips. These particular dips that I've highlighted for you are dips due to hydrogen. But if the same star were moving away from us, then we would see a very similar spectrum. This is just another word for spectrum for this little rainbow here. And we'd see the intensity shifted a little bit to the right. And you see that this red curve, which has everything shifted a little bit to the right, has exactly the same dips as the original black, or in this case, the gray curve, but all of them are moved a little bit to the right. And since we know this formula up here, in principle, we could use this to find out how fast the object was moving with respect to us. And that's something that we'll be covering in this notebook right now. Right, so if I can go into the next notebook. Right, this is the radial velocity activity. So I'm going to assume that everyone is able to see my screen. Should I zoom in a little bit, perhaps around this? Is that good? Yeah. Okay, great. So we're going to do something very similar to this. We're going to look at the spectra of some stars, and we're going to try and measure how fast they are moving with respect to us. So we start off this notebook by importing NumPy as NP and importing matplotlib.pyplot as PLT. We've already done this before in previous notebooks. So these are the two packages that we'll be using today. So if we go back to our data, just a second, I'm just going to reduce this a little so that it doesn't block my Zoom tab. Now, if we go back to the SIP workshop folder, we're in the programs folder. And if we go back up, we have, of course, the data folder here. And in this folder, we've already discussed the different templates and the different catalogs that are there, but we also have some other files here. So for example, we have 3 of these files that start off with a number on the top, and then an underscore and spec.txt. And then later on, we have some files that have a TMPL, which I'll come back to in a few minutes. So these are the spectra of 3 stars. If you look at the numbers that are over here, 600, etc., 4761, etc. And if you go back here, you'll see that that's exactly the number that's over here. These are the details of the spectra of these 3 stars that are there in these separate files. And our task today is to measure the radial velocities of these stars using a method very similar to the one that I just described in the presentation. So the first thing we need to do is to incorporate that formula, which takes a rest wavelength, a wavelength of a star, if it were not moving with respect to us, and transform it into a wavelength that we would see if the star were moving away from us at a velocity v. And we do that using the formula that was given in the slides. And so we're going to do this here. So let's start off first by defining the constant c, because it's going to be helpful because we're going to use it. So we can just define c as the actual number. I don't remember this. I'm actually looking it up. We're going to write these numbers in kilometers. Is that a question? Or is okay?
No, I think Raja was unmuted. Yeah.
Okay, so these units, the current units here that you know of the speed of light, some of you might know it as 3 × 10⁸ meters per second. We are going to write it out as a little bit more precise, 299,792, but we're also going to write it in kilometers per second because these are the units that are most natural for the rest of the problem. And so this is the speed of light in kilometers per second. And now we can see mu lambda, which is the wavelength that we will receive from the star. Because it's moving with respect to us at some speed v. And we're going to get this by multiplying the rest lambda, which we put in here, the rest wavelength. We're going to multiply this by 1 plus v by c. And if we do this, we can call this function shift to moving along with some rest wavelength and some velocity v. And what this function will do is it will first compute nu lambda by taking rest wavelength, multiplying it by 1 plus v by c, and then returning this to us as a number. Okay. So notice again, as Logic described, there are these nice little doc strings over here. So I can show you why these doc strings are nice in action. So I'm just going to create a small cell setting. And let's say, much later you go back and you want to find out what this shift to moving function does. You could just do a help shift to moving. And it shows you the doc string, the little string that's underneath the name, which tells you that this is a function to shift a wavelength array using the Doppler equation. Anyway, so this is just a small example of that function. So now let's actually try and test this function, the shift moving function. And we can do it by, and so what they've asked us to do here is to fill in code to test this function with two velocities, one a positive velocity of 200 kilometers per second, and a negative velocity of the same magnitude. So let's see what happens here. So while I'm typing this out, what I'd like you all to ask yourself is, if the velocity were positive, should I get a wavelength that is larger or smaller than the wavelength that here? So the wavelength that we're dealing with is a very famous wavelength, the wavelength of hydrogen alpha, which is 656 angstroms. So I should actually put down here in angstroms. So how would I do this? Well, I would call the shift. Let me just define a new wavelength to be plus. Oh, okay. Let me just call it shift. It's 200. Let's just call that plus 200, which is first wavelength. And I'm going to just call the shift to moving function with the rest hydrogen alpha wavelength. So I'm just going to say rest lambda is equal to rest h alpha. And with a speed that is equal to 200. And I can now try and print this number out. And the good thing with the print function is that you can print multiple things right next to each other. So for example, I could say the wavelength when v equals 200 kilometers per second is, and then it will print that line and then the plus 200 immediately after. And so you can see that when the wavelength is, when the speed is 200 kilometers per second, the wavelength is 6567.3 and so on, many different decimals. And you can see that if we originally started off with 6563, when we have an object that has a positive velocity, in other words, it's moving away from us, it gets red shifted. In other words, it moves towards a larger wavelength. And that you can actually see here because we go from 6563 angstroms to 6567 angstroms. Now we can do the same thing. We could go to a minus 200, which we would then say shift to moving with a rest lambda that is equal to rest h alpha. So it's the same wavelength, the same rest wavelength that we had in the previous example. But now we'd send in a speed of minus 200 kilometers per second. And just as before, I'm going to type out the wavelength when e equals minus 200 kilometers per second is, and type in 200. And now when I do this, you can see that when V is 200, you get a 6567. But when V is minus 200, you get a 6558. In other words, we've gone down. Our wavelength has reduced. In other words, it's moving towards the bluer side of the spectrum. And therefore, this is a blue shifted. And so, of course, this should make sense to everyone. If anyone has a question, you should ask here. I can't see the chat, so if someone can look at that and tell me if there are any questions there.
No questions so far.
Great. Okay, so that's good. So, so now we've tested our shift to moving function. And now what we're going to do is we're going to do two things. We have a star. We need to find out whether it's a main sequence star, the MS that Lodrick showed us, an asymptotic giant branch star, an AGB, or a red giant branch star, an RGB. So the first thing is to find out the type of the star, but we also want to know how fast it's moving with respect to us. So first of all, let's load a star, and then let's load a template. And I'll first describe how we figure out the type of star, how we have a guess for the type of star. And then we'll try and see if we can figure out how fast the star is moving with respect to us. But in order to actually know what the type of star that we're dealing with, as we've seen earlier in the color magnitude diagram, there are very clear sort of boundaries that are established by these different stars. Now that translates to certain similarities in their spectrum. Of course, every star is different, and so every spectrum of a star, in other words, the rainbow that they produce, is different. But there are many similarities between them. So what we're going to see here is that we're going to compare the spectrum of our star with a template spectrum. In other words, a spectrum, sort of an average-ish spectrum of stars from either the main sequence, the AGB, or the RGB branches. And we're going to see which one matches the best. So with this, we'll be able to guess both the type of star, the classification of the star, as well as its speed, which I will show you next. So I'm going to put in a name of a star. So for example, let's try this particular star, the last one, which is phone in 1022. And let's just put in the first template. It could be MS, RGB, or AGB. I'm just going to choose MS right now. And what's going to happen now is that the science file, which is the spectrum of the star, is going to be taken from where in the programs folder. So we go back up, we go into the data folder, and we have the star name underscore spec, which I showed you right at the start. And it's going to say that that's where the data is for the star. And the data for the template has the template name, in this case, MS underscore TMPL. Then it loads both of these files. It loads the science file and unpacks it, meaning that it takes every column of the file and takes the first column and stores it to the first variable, the second column and stores it to the second variable. So if I go back into that file, you can take a look at what it looks like. So for example, this is the star we're looking at. And in Jupyter Notebook, you can see that this file only has two columns. The first column over here are all the wavelengths, and the second column are the fluxes, in other words, the intensities in some sense of these different stars at those wavelengths. Similarly, we have exactly the same thing for the template stars. So if I run this cell, I'm going to load all of that data, and it's going to be stored in these different variables. And now we're going to deal with, in some sense, the most important part of the code. So the first thing we're going to do is we're going to keep the guess velocity of the star to 0. And we're just going to plot the template in black and the science spectrum in red. And we're going to see what they look like on top of each other. And we'll see whether there are any general features that we can tell. So I first create an empty axis like we've done before. I then plot on that axis the template flux. And I make sure that its color is black, and I add a little label that says template with the name of the template that I've chosen. And I do the same thing with the science, with the spectrum, and I put in the star's name right after that. And this will set the X and Y labels. So I'm going to run this now. And if you guys run this as well, you should be able to see something that looks exactly like this, with the relative flux on the y-axis, lambda in angstroms on the x-axis. And you see the star here. And so the first question to ask is, do you think that this is a good match? Like, if we look at these two spectra, do we see any general features between the two of them that are similar? So I'll let you guys answer on the chat, and Aprajito, if you could tell me if anyone answers on that. I mean, do you think this is a good fit or not? Do you see any similarities? Do you see any differences?
Do you think the red line and the black line will line up well? That's the question. Okay, one person says no match.
No match.
Another
Yes.
person says, I don't think it's a good fit because the slopes of the lines are so dissimilar.
Yes, and that's true that this initial region of the graph here does seem to have a very different slope. So it looks like our template might not be the right template. Remember that the Doppler effect, the fact that the star is moving, is only going to shift the template leftwards or rightwards. So let's see what happens if we choose a different template. So let's now try an RGB template. So if I run this, and I go down here, now, what do you guys think? Do you think this is a better fit? Do you think this is a worse fit than before? Well, I mean, it's probably not a worse fit than before. That much is clear. This certainly does look like a better
People are
fit.
saying it's a better fit now. And
And
they
so
are
for
saying that it looks similar. Yeah.
Exactly. So you see that there's a little hill here, and both the template spectrum and the science spectrum seem to have this little hill, and they have this little hill as well. The general value of the relative flux is also more or less the same. And so of course, remember that the template was not going to match exactly because every star is a little different, but there are general features in these stars that are related to the physical processes that are occurring in these stars, which do seem to be matched. But let's make sure that it is, let's compare this again with the AGB so that we can cover all our bases. And then we run this for the AGB. And now you see that again, the template, which is the black curve, has changed. The general level is, of course, roughly the same, but you see that many of the features are still very different. I mean, there are many features in this spectrum that are in the science spectrum that are not there in the template. And so the best match, if we only have these three options, the best match that we have is, in fact, the RGB template, which I hope everybody will agree. And so if I go back down here and I look at this, I see that at least the features do match, but they don't match perfectly. There are certain variations here and there. But now what we're going to do is try and guess the speed of the star with respect to us by trying to shift the stars, by trying to add a velocity to it and see whether the template and the star spectrum align perfectly. So the first thing,
Philip, I was going to suggest something very quickly before you shift, is to zoom in.
Yeah, exactly.
In wavelength between, say, 7,000 and 7,200 or 7,000, 7,300. That
exactly, yes.
And then people can see that that there is a horizontal shift between the black and red lines.
Exactly. So I'm going to do exactly that. So just by looking at this, of course, we get a sort of global view of the spectrum. But what we really want to know is how much we need to shift. So we want to see small differences between them. So what we're going to do is we're going to stake the region around this part, 7,000 to 7,200 roughly. And we're going to zoom into that region. So we're doing that by setting the x-lim of my graph. And to do that, I say ax.set x-lim, and then I put a lower limit and an upper limit. And when I run this, you should see that the plot will change. And you see that the plot has a lower limit of 7,000 and an upper limit of 7,200. And so now you can see that they do have general features that are similar. They don't look exactly the same, but the general trend is similar. And now the question is, how do I move this black curve, the template curve, so that it sort of aligns better with the science curve? And so one thing I'm going to do is I'm going to look over here, and I'm going to see that both the template and the science have a peak here, right? So I'm going to ask myself, what do I need to do to bring the template back so that it can fit on top of this little like science peak here? So if I want to move Yes.
And Philip, sorry, it's not just those two peaks are a great one. And look at the dips on the just to the right of that. The dips also don't agree. But the black dip and the red dip are similarly, the black dip is to the right of the red dip. Not that dip, but you know how the first of the dips, there, exactly. The black dip and the red dip are misaligned in the same sense. Black is to the right of the red, the peak is to the right, and you can see that with the other two. These are, by the way, these are produced by titanium oxide in the star.
Right. So
yeah, exactly. Sorry, please go ahead.
I'm just now going to try and move the template star. I'm going to try and move its spectrum a little to the left. And to the left is, of course, lower wavelengths. And so I'm going to move it. I'm going to blue shift it, which means I need a negative velocity, because I try to remind you that a positive velocity is a star that's moving away from us, and a negative velocity is a star that's moving towards us. So some people have suggested minus 160. Let's see what we can do if we can put in minus 160. Let's see. If I try with this guess, okay, not bad. I think it does seem to be matching, but I think we can probably go a little bit further. I think we can try and get these dips to move a little bit more, but let's try a little bit more than that. Let's try minus, let's say 200. Let's see what that looks like. Right, so this matches. This peak seems to match quite nicely here. The valley also seems to match a bit. That's true. There's of course small variations here and there. This peak also seems to be aligning quite well between the two stars. And yeah, so I think this sounds like it might be a good fit. Raja, what do you think? See it out? No, not right. That's fine. But I think that this would be a generally good fit. Of course, a lot of this doing it by eye is not how people do this, right? I mean, they have hundreds and thousands, millions of stars in these galaxies. And to try and know how much each of them has to be shifted by is very difficult. And it's certainly not something that can be done by the eye very accurately. So of course, there are algorithms that are used that can actually find the optimum shift that you need to move something. But this is essentially what we do. So I'm not going to do another star unless someone thinks it's a good idea, but I think we can sort of move on because we may not have too much time. I think.
I think that's for the best.
Right. But I would urge you all to go back and try and choose another star here, choose a different star name, and put in a different temp, and then try and see whether you can find out which template matches which star, and see whether you can find out how fast it's moving relative to us, and using pretty much the same technique as this.
By the way, a quick note on the AX dot function name format there. You've only encountered PLT dot plot functions, but here AX is essentially an axis object. And the hierarchy in Matplotlib is that you create a figure object, and each figure object can contain multiple axis objects, and each of those axis objects can support multiple lines, dots, text, stuff like that. So here we have defined an axis object, and then we are plotting the lines to that axis. Okay, you can think of the figure as sort of the paper that you're drawing a plot on, and axes are, the set of axes that you have drawn, that you will be using, the grid lines that you'll be using to, plot your points if you're doing it by hand. Yeah, back to you, Phil.
Great. So once you're done with that, you can fill in all of the data here, just so that you have records of what this particular star is, what template it has, and what velocity it is. And I just want to point out that we've got two things. We're just looking at the spectrum and comparing it with the template spectrum. We found out two things about the star. We found out what classification it is and what its velocity is. That's quite interesting. But now what we're going to do is, all of this has already been done for us in some sense, and that's in the data that I think Roderick already showed, which is this particular file, which we will be loading in. And if you notice in this file, it actually has a specific column, which is the velocity of the star in kilometers per second, which they do in computational ways, which we come up, which they compare spectra and find these quantities for all of the stars that are there in this catalog. So what we're going to do is, again, just as we did in the last notebook, we're going to read in this data just as before using the np.loadText function, which again goes back up, goes into the data folder, gets the kehxt data.txt file, and unpacks, that is, takes every column and puts it into every one of these different variables. And now we have our results. And what we would ideally want is, as is described in the title here, is a radial velocity map of Andromeda, which means that with all of these different velocities, we now want to know, given a certain position of an object in Andromeda, how fast that particular star that's at that particular position is moving with respect to us. And so we're going to try and make this plot. But before we make this plot, we need to convert a couple of things because, of course, we're on the Earth and we're looking up at the sky. And so what we can actually measure, the distances that we measure are actually just angular distances. This is an object here, an object somewhere else there. And so we would first need to go from these little angles to physical distances. And we do that using this degree to kiloparsec conversion factor. And then we take the psi and eta, which Aprajito described earlier as being the coordinates with respect to the center of Andromeda, and we multiply that by this degree to kiloparsec, so that what was originally psi and eta were originally degrees. We have now multiplied them and gotten them the velocity. So in the earlier CMD exercise, we were using these filters and so on. Right now, we're just going to be using the velocity and psi and eta, and we're going to plot a little scatter plot of them, which you might remember from your first notebook. So what we do is we first again define an empty axis, but this time what we do is we make sure that the aspect ratio of the axis, in other words, the number of units, that we keep the same number of units on the x-axis and the y-axis. So the same unit of distance in each of them. And we then set the x label to be psi in kiloparsecs, and the y label to be eta in kiloparsecs. And then we set the x and y limits, as I've just shown you earlier, to 15 and -5 and -10 and 15. This is all just to make the plot a little pretty. And then we plot a scatter plot. So this is going to take a little bit of time. I'm just going to spend a little bit of time here because I think you guys should understand how to plot this. So when we plot a scatter point, we can send in two lists. On the first list is the x-axis. The second list is the y-axis. So in this case, we have psi on the x-axis and eta on the y-axis. And then over here, we can, and this will plot a single point for every one of those x, y coordinates. But now we have a third possibility. We can also change the color of those points. And what we're going to do here is that we're going to set the color of the point to be related to the velocity of that particular star from the catalog. We can also decide the size of each of these different points. And right now, we've set all of them to have exactly the same size of 5 units in Matplotlib's units. And we don't want any border colors around it. And then there's a Vmin and Vmax, which I'll come to in a few minutes, and a color map, which again, I will come to in a few minutes. So I'm going to run this site now, and you should be able to see, I've not run the previous cell, sorry. So you should run the previous cell and then run this, and you should be able to see a nice little color bar. So a nice little scatter plot over here, where you have a large number of points, and each of those points is a different color. And this color, as I remind you, is related to the velocity the star. Now, I don't want all colors to be plotted. So I'm going to say that there is a minimum color of -700, and that's the number that's down here, and a maximum color of +100, because I know that there are very few stars. There might be a couple, for example, that have very, very high velocities or very, very low velocities. And if they exist, then the color bar that I have over here would be very stretched out, and I wouldn't be able to see interesting things. And so I set a lower limit and an upper limit for this. And then I also have a color map. And the color map is going to tell me what color corresponds to what velocity, more or less. And this particular color map, which is called Viridis, goes from blue at one end all the way to yellow at the other end. And we can try using different color maps, and we will actually in one of the next cells. And I actually want to put in a color bar, because if I just got this graph without a color bar, I wouldn't know what would correspond to, what does this particular color correspond to? Okay, great. So now that we have this particular color map, we now need to label the parts of this plot as either being blue shifted or red shifted or neither, with relative to the center of the Andromeda galaxy. Andromeda galaxy is M31. So some people have asked, what would happen if I change Vmax to 200? Why not? Why don't I try it? Let's just set it to 200 and run it. Now you can see that 200 is up here. So what can you see is different? So the maximum value is 200, but you see that variations over here are no longer so visible. So nothing has actually changed, but it perhaps is not the most obvious to see differences and see variations in velocity as clearly as possible. So you should fiddle around with these and find the numbers that look the best for the plot. So now that we have this particular graph, let's actually try and see which parts, let me ask this out as a question. Yes, someone's raised their hand, yes. You can unmute yourself and ask the question.
Sorry. So I was just wondering, where are good places to get data like this from? Like, say, if I want to make a radial velocity graph of like Centaurus A or something, where would we find that kind of data?
Very good question. I don't actually know. This isn't my specialty, but Raja would probably be able to answer that much better. So if he's
Thank you.
around, he might answer now. Otherwise, I will remind him and we will get back to you. Any other questions? Okay, so then let's move on. So let me ask this question out to everyone. Which part of this, so you all see that this is, of course, a section of Andromeda. This is a section of a disk that we're looking at head on. And it's slightly, so you can imagine the galaxy as being a sort of frisbee, which we will see in the next notebook. And you can now imagine that this frisbee is slightly tilted. And the minute it's slightly tilted, you'd see it to be a sort of ellipse. And so that's sort of the ellipse that we're seeing over here. And every dot here represents a particular star. And there are regions, for example. So if you look very close to 0, 0, this entire region here, there doesn't seem to be any data. And that's because this particular region has so many stars so close to each other that we can't actually tell them apart very well. And so we don't have much data over here, but we have data for the remaining part of this region. So let me ask this up, which of these regions do you think would be moving towards us? Which of these regions would be blue shifted? Can anyone tell me that? You can answer in the chat. I think I can see the chat. Anyone? So would it be the region around here where I'm pointing, or would it be the region around here?
Somebody says the more lighter green section towards the top.
Okay, so now let's look at that. So if it's blue shifted, if it's moving towards us, then that would mean that it should have a very negative velocity. If you remember, the way that we've defined our velocities is that a positive velocity is moving away from us. And so if it's in the lighter green section, we're at minus 100. So yes, it's not at plus 100, but it's at minus 100. So yes, it is blue shifted, but it is not the most blue shifted. As you can see, this particular region over here at around minus 700 is in fact blue shifted. So you can see that the bottom right region is in fact blue shifted. So let's actually try and put in a little bit of annotations on these graphs, which are also very useful when you make a scientific graph, is to actually put in annotations. So I'm going to put an annotation using a function called the ax.text function. And what this, okay, let's say now, let's say you don't remember what the ax.text function accepts. Something you can do is you could just run this in a new cell. You could run in ax.text with a little question mark at the end of it. And that will pop up this little pager down here, which tells you all about the function. So it tells you that ax.text accepts at least 3 variables, an x coordinate, a y coordinate, that's where the text is actually going to be specified, and the string that you actually use for the text. So we're going to use this right now. So I'm just going to remove the cell, and I'm going to actually just a second. Yeah. I'm just going to type out ax.text, and I'm going to put a little note, say somewhere around here, that says blue shifted. So what would that be? Its x coordinate would be around 0, and its y coordinate would be around, I don't know, minus 8. Let's try that. So at x coordinate of minus 0, of 0 and y coordinate of -8, and a string that says shifted. Okay, so I can now run this. Okay, good. It's sort of okay, but I think I could move it a little bit lower and a little to the left. So let me send -2 and -10. Oh, that's not good. 2 and 10. Yeah. So there's a little bit of fiddling around here, and I can get it. There we go. So I get it in around the right region here that says this. Okay. So now we have a little bit over here that happens to be blue shifted. I can also change the color of the text. I could do that again by making this say blue. Why not? Right. And I could also put some other text now. So if this region is blue shifted, the other region, which is predominantly like it has a much lower negative value. So in the sense that it's only at around -100 or so, this entire region is is more red shifted with respect to us. So I'm going to put a little bit of text that says red shifted at around, say around here. So 3, I think 10. That sounds good. So I put it here, say 3, 10. That says red shifted. And I change the color to red so that it says, there we go. So we have blue shifted over here and we have red shifted over here. And somewhere in the middle is a region that isn't neither blue or red shifted. So let me just copy this down and put that down. Say around this region here, which will be around 0, I don't know, 2, I suppose. 2. Oh no, 2 will be probably too close. -9. Yeah, let me just make this blank. Okay, right. So we have a region that's blue shifted, a region that's red shifted, and a region that isn't either. And of course, you've got to remember that this is an entire disk, and this particular disk has. These are the velocities that we actually measure, the absolute velocities of the star. But these aren't the velocities with respect to the center of the disk. So now you've got to ask yourself, how is this disk actually rotating such that this region ends up moving, with a velocity of 100 with respect to us, and this one ends up moving at a velocity of -700 kilometers per second with respect to us. Okay. So this is, of course, the center of Andromeda, which is moving, which is neither blue or red shifted with respect to us. And this is more blue shifted with respect to the center. And this is more red shifted with respect to the center. So this region is moving away from us, and this region is moving towards us. Does that explain to anyone? Does anyone have any more questions about this?
We will go into a bit more detail about this and the following astronomy section. So, yeah.
Raja. Yeah. So, of course, what we've done above here is using this this particular color map, which is the Viridis color map, which goes from blue to yellow. But you might want to do this in a different type of color map. You might want to do this in a color map that goes, say, from red to blue or something like that. And you can find out a lot of color maps from this particular link. You guys can go up there yourself. So I'm going to make another tiny plot here that changes the color map from Viridis to the red-blue color map. And okay, let me just first use the red-blue color map. And what happens with the red-blue color map is that you have the colors going from red to blue. But what this does is that it puts red at the bottom and blue at the top. But that's not what we want, because we want this region to be redder because it's red shifted, and this region to be bluer because it's blue shifted. So one way we can do that is to reverse the color map. In other words, look carefully at this region. You see that it goes from red at the bottom to blue at top. Now I'm changing the color map to put an _R in front of it. When I run this, you see that the order of the color map is changed. And so this region, which is of course redder, has been red shifted. And this region, which is bluer, is in fact blue shifted. And what is neither is pretty much white in the center. Okay, so I think that covers this notebook.
So I've been explaining NAN, what NAN is. NAN is something that we'll find in some of the catalogs and some of the data that we've been using. NAN stands for not a number, and it is a special value in computing, in coding, including in Python. And it's basically like a placeholder value for databases when there's no data at a certain position in the database. You can't really put 0 in there because 0 itself is a number and it's itself a value. You can't really leave it empty because how do you define empty in a list or an array? So you put in nan. NumPy introduces the nan value into Python, and the magic of nan is that you can multiply, add, or otherwise operate any number with it. It will return nan, okay? Because that's what it's supposed to. Because if you're trying to do math without a number, what are you supposed to find? You're supposed to find something that's meaningless. It's not a number. So it's something that, fills in the gaps in a database and makes sure that the arrays are all of the same size. Because like we discussed before, for some functions like the plot function, arrays of different sizes will cause trouble. And nan kind of prevents that. There are special functions within NumPy that specifically deal with arrays that have nan values that will calculate things by ignoring the nan value. For example, if you just pass an array with the nan value to the np.max function, it will by default return nan, okay? And if you don't want it to return nan, if you want it to return the actual finite number in that array that contains nans, you have to use the np.nanmax function. Pretty sure that's the name of the function. Anyway, this is a class of functions within NumPy that deal with nan. Anyway, that's nan for you. This question, can we get the Jupyter notebook with those codes just for future reference? You can find the complete notebooks in the PyaR website. The complete notebooks are available with everything, included. Yes, thank you for linking that. Any other questions? Feel free to post them to the Slack. There have been some questions about where we got the data from. Well, this is HST data, this is Hubble Space Telescope data. And Raja will cover the background of the survey in the very last astronomy section, which will be at the very end of this session, a very brief section, a very brief astronomy section. I think that's 5 minutes. So I should be getting back to business now. Let me fire up my Chrome window. And
Aparajita, I missed if you said something. I heard my name, but I didn't quite catch what you said.
I said you will have a section at the very end of this session that covers the survey, the fact survey.
Yes, exactly.
Is that right? Yeah.
Perfect. Thank you.
Okay. Let me share my screen. Here we go. These are Raja's beautiful slides. We'll skip a couple of slides. They go into the Milky Way galaxy. They cover the Milky Way galaxy. You know the Milky Way galaxy. You all live there. I hope you know your way around. Anyway, so we're not dealing with the Milky Way galaxy, which looks like this. And this is an artist's impression because we have never been outside the galaxy that we live in. This is huge, it's massive, and it would take forever to fly out of the galaxy and click a picture from there and then send it back to Earth. So the sun is somewhere here in the Milky Way galaxy, and from there we are looking at a nearby galaxy called the Andromeda galaxy, and that's galaxy that we've been observing all this time in this through these tutorials. That's where our data is from. All the stars that you see were stars from the Andromeda galaxy, which happens to be the nearest galaxy to us. And as you have already seen, the Andromeda galaxy, the starlight from the Andromeda galaxy is overall blue shifted, right? Which is odd if you know anything about how the universe works, because we expect all the galaxies in the universe to be flying away from each other because the universe is expanding. Okay, which means that the Andromeda approaching us is an anomaly. And if you actually play it out, if you create a simulation of what happens when the Andromeda keeps approaching, because there is no sign that it's going to stop, you will know that the Andromeda galaxy is actually on a collision course with the Milky Way galaxy, with our very own Milky Way galaxy. And here's a little movie made by the people at Space Telescope Science Institute using Hubble data. These are two simulated galaxies. These are two simulated spiral galaxies. They're called spiral galaxies because they're shaped like a spiral. Each of these galaxies contain billions, I think trillions of stars. These two galaxies look very much like our own galaxy, Milky Way, and our nearest neighbor, the Andromeda galaxy. So you can see that these two galaxies are approaching each other, and this is a movie that, fast forwards a lot in time because this actually happens over billions of years, right? This literally happens over billions of years. So let's see what happens when we let them collide. Okay, so they haven't collided yet, but here we have paused and we're looking at an actual image of two galaxies, two very distant galaxies, not our own, not Milky Way, but two other galaxies. And you can see that they look exactly the same as the simulation. So that's how we know the simulation is valid. It is valid, and it gives us predictable results because this actually happens in nature. And if you let it play out, and you can see that the camera is flying around, we are looking at it from different angles, and please note how the disk looks different from different angles. Once again, we're changing our perspective, and once again, here's the real picture of two colliding galaxies. And you can see that when we look at the galaxies from edge on, they seem thinner, and they seem more like lines. And when you look at the disk head on, they seem more like circles. And if you look at it from any angle in between, they will look like an ellipse. Okay, so the simulation is running, and you can see more examples of galaxies that are currently in the process of colliding. Very, very distant galaxies. All of these are other galaxies, not our own, nor the Andromeda galaxy. This is much like evolution in biology. You have a theory of natural selection. You have a theory of how one species has evolved from a different species, and you go looking for fossils. So just like paleontologists, astronomers also go looking for evidence, and we look for evidence using a telescope. All right. So in the last notebook, Philip mentioned that one part of the galaxy actually moves much faster. It moves towards us at a higher speed than a different part of the galaxy, right? So why is that? Because the entire galaxy is approaching us, right? It's not like one part of the Andromeda galaxy is tearing away from the rest and approaching us. And the rest is just kind of sitting there. Or like, there's some kind of shearing going on. None of that, right? What's actually going on is that it's rotating. Spiral galaxies rotate. And as we saw in the simulation, the two galaxies were rotating. They were spinning, right? They were spinning disks, which means if you look at the disk, right? If you look at a disk, say my phone is a disk, okay? Say my phone is a galaxy. You can see that if it's moving towards you, the whole thing will have the same speed, right? But if it's rotating, you'll see that the camera end of my phone is moving at you at a higher speed than the bottom end of my phone, right? Okay, so that's how the rotation actually changes the observed velocity of the stars in Andromeda. And this is basically the plot that we're looking at. There's the heliocentric velocity, which is the velocity with respect to the sun, okay? Not the Earth, because the Earth is going around the sun, so we don't want to, bother with that because it changes throughout the year. And this, actually, if you look at it carefully, you will see that this image is basically patchy, right? This doesn't look like a solid ellipse. And the reason is that we don't observe all the stars. We observe small blocks of the stars, blocks of the galaxy, small rectangular patches. We zoom in, we look at a few hundred stars for each observation, and we'll then look at a different part of the galaxy. Okay, so these are multiple little pictures stitched together. That's the way to think of it. And this only shows half of the galaxy, the top half, okay, the northern half. And you can see, you can vaguely make out an elliptical outline. If you imagine the center to be somewhere around here, then this is the top part of the galaxy. And if you follow my cursor, that's kind of the top part of the ellipse, okay? Vaguely, right? And now you know which parts of the galaxy are actually moving away through rotation, even though on a whole they are moving towards us, and which part of the galaxy is moving towards us through rotation at a faster speed. Yeah, I will skip the rest and hand it over to you, Philip. I'll share a couple of links in the Slack about these simulations. And I'll share these slides. Okay. If you have any questions, please post them in the Slack. I'll keep an eye on.
Right. Can everyone hear me?
Yes,
Yes.
we can hear you. Yeah.
Okay. So so now let's do activity 5. And this particular activity deals with another small Python file, which I will show here just a second, which you can find inside the same folder as all of the different notebooks, which is the fake disk.py file. And what we're going to do is in the next two notebooks, this notebook and the next one, we're going to talk about the dispersion of velocities. In other words, in the previous notebook, we just looked at what the velocity was. And now we're going to start asking ourselves, what is the range of possible what is the range of the variations in the velocity? And so we're going to start talking about that. But before we start doing it, we're going to start simulating a fake disk. Okay, so this is going to be a little like fake galaxy that we're going to make. And we're going to do this using this package that is this little Python file that has already been provided to us. And you'll notice immediately that all the other Python files that you've been using are IPYNB, which are interactive Python or Jupyter notebooks, while fake disk is a .py file. It's a slightly more old-fashioned notebook. Python file. And when you open this file, you'll see that it looks very different from the other files that we've been working on so far. You don't need to edit this file at all. I'm just going to show you what it is. And we're just going to use this file. So this can be thought of as a tiny little module that somebody else has made for us. And what we're doing now is we're just using the functions that are there within this module, and we're going to use it to get results. So let's now open notebook 5, which is the simulated disk activity. And so what we're going to do is we're going to simulate, as it says over here, the disk of Andromeda. And so we start off by importing the standard functions that we need, which are numpy, matplotlib. But we also import this from fake disk, import fake disk. So in other words, the fake disk.py file, we're going to import it as if it's a library So it's not library like NumPy and Matplotlib, because these are libraries that have been created by other people. Fake Disk has also been created by other people, but if you were to create a library like Fake Disk or some small set of functions that you would like to use, well, you can then create these functions, place them in a .py file and place them in the same folder, and then you could reuse these functions repeatedly. Great, so I'm going to run this, and there's going to be no errors because Fake Disk is in the same folder. And now I'm going to start looking at a couple of other functions that we've defined in this notebook. So the first function is the show map function. There's actually not going to be too much in this notebook that you need to do like in the previous notebook or in the next notebook. So this is, you just have to run the cells and sort of understand. So I'm just going to walk you through what every one of these cells does. So the show map function takes in something and a specific quantity and a label and a couple of other parameters, and it produces a color map, a plot essentially for you. So again, it creates some axes just as before. It sets the X and Y labels of these axes just as before. It sets a title that says simulation. It sets the X and Y limits from the maximum and the minimum values of the quantity that you're sending in. It also has a little flag in it that's called cutout, which if it happens to be true, it will clip into a mystery cutout, a little 1/4 section of this entire graph. If not, it's going to just plot a scatter plot just as before of the X and Z. I mean, Z essentially is Y for us. If you're more comfortable using X and Y, you can use that over here. But right now we're going to use X and Z because that's what these the Fake Disk function also gives us. And then you pay attention to what happens right here, which was earlier. What did we do? We plotted every point on a scatter plot in the previous notebook to be the X and Y coordinates of that point, and its color to be the velocity of that point. Here, however, we're setting the color to whatever the quantity is that we're sending along with show map. And I'm going to show you what exactly that does later. The rest of the parameters are the same as before, and then we add a color bar just as before. So I'm going to run this cell. And now we're going to create our fake disk. And we're going to create our fake disk by using the fake disk command that we have imported right up here. So before we create this fake disk, we need to decide a couple of parameters. I'll go back and slowly sort of adjust a couple of these parameters so that you see the different factors here. Someone has asked about Vmin. I'd like to point out that Vmin is actually not the lower velocity or the higher velocity. It's the range of the color bar. It could be from -700, could be from -200. So it depends a lot on what the quantities are that we're sending into this function to plot. And you will see that the quantities that we're actually going to send in there are probably not the velocity. So you're going to see that in a few minutes, and this will become clear. So let's just create this. So we have a bunch of different factors here. We have a scale factor, we have a dispersion, we have an inclination, we have a position angle, a rotation velocity, and a number of points. So I'm going to walk you through every one of these different things, but basically all of these different factors go into the creation of the fake disk. And then we create a fake disk, which we will call sim, which is our simulation. So let's go backwards. So n is, of course, the number of stars in our disk, and it's an integer. And in this case, we've chosen it to be 10,000 stars. V-rot is the rotation velocity of the disk. The position angle is another angle that sort of measures the orientation of the disk. A more interesting angle is the inclination. So we have to notice that our disk here is essentially a frisbee. So it's a nice little circular frisbee. But it's a frisbee that isn't necessarily oriented completely flat towards us. It's slightly tilted. And when you look at even a circular frisbee that's slightly tilted, it will look like an ellipse. And that's going to explain what you see when I run this cell. So let me just actually run this cell right now. And if I do that.
Philip, at some point,
yes,
I will explain. I'll try to provide an intuitive feel of what PA is and what inclination is. Inclination is a little easier to explain, but I'll try to provide an intuitive explanation of those two things. I don't have to do it right now. You tell me when and I can jump in.
Right now would actually be good if that's okay with you.
So when you see in general, as Philip just said, when you see an inclined disk, it looks like an ellipse. one can ask the question, how do I go from a face-on disk? I'm sorry if you can't see me, just give me a moment, I'll turn my video on. One can ask the question, how does one go from a face-on disk to the orientation that we currently see? Like you're seeing an ellipse in what Philip is sharing. But if I started with a face-on disk, it would look perfectly circular. It wouldn't look like an ellipse. So we have two choices, two decisions to make. When you start with a circular disk, how do you turn that into a particular kind of inclined disk? One choice you make is along what axis should I rotate this disk? Right? I mean, along what axis? If I chose an axis that runs from upper left to lower right, and I chose that axis and I tilted the disk about that, I rotated the disk about that, that would be a particular choice of angle. That angle is called the position angle. How much you tilt by is called the inclination. So when you have an inclination of 0, there is no meaning to the position angle because you've not rotated the thing at all. The moment the inclination is not 0, the moment it's non-zero, that is you're tilting the disk slightly relative, even slightly relative to face on, then you've made a choice of axis about which to rotate, and the amount by which you rotate is just called the inclination. So the way I like to think about inclination, between any two planes, the inclination is defined as the angle between the perpendiculars to the angle between the perpendiculars to two planes is defined as the angle between two planes. In our case, it's not the angle between two planes, it's the line joining us to the galaxy. That's one line. And the other line is the line that's perpendicular to the plane of the face of the galaxy, the plane that defines the face of the disk. So you can imagine that in a face-on galaxy, the perpendicular to the plane is the same as our line of sight. So inclination is 0. There's no the 0 angle between those two lines. And conversely, when the disk is perfectly edge-on, then the perpendicular to the plane of the disk is at 90 degrees to the line joining us to the galaxy. Anyway, those are the only things I was going to say about PA and inclination angle.
Great. So I've put back the inclination angle to, I think it was 77 point, and this is PA. And now when I run this, you see that you get back this little ellipse, and you should be able to remember, I mean, you should be able to imagine that this is actually very similar to what we were seeing in the previous notebook and what we will see in the next notebook. This is very much like the Andromeda data that we got. Of course, this is a simulated galaxy, and so it has a lot more data points. We can also change some of these numbers here. So I could change 10,000 to just 100, and I'd just get 100 different points. But of course, you can't see anything very clearly because there are very few points here. But you can make it, 1,000, and you'd see more points, and you can go back to 10,000, and you will see it. Something that's very cool in Python is what I always have trouble with is actually knowing how many zeros there are. And so something that you can do in newer versions of Python is that you could replace what you would normally do with commas. You could put little underscores here, and those are also perfectly valid Python numbers. So Python ignores the underscores, so they can be used by you to know the difference between certain numbers, so you won't make mistakes in orders of 10. So we've got this little simulated disk for our galaxy here. And now what we're going to do is we're going to try and create what is called a dispersion map. In other words, we've got a range of velocities. Notice that these are, of course, radial velocities. In other words, they're the velocities towards or away from us, because these are the velocities that we can measure using the Doppler shift method. And so what we'd like to do now is ask ourselves, what exactly is the range of velocities about a certain point? In other words, if I was sitting at some specific point, let's say 0, 0, right here, and I took a little circle around me, like I drew a little circle around me of some size, and I take all the stars in that circle, and I ask myself, what is the range of possible values that I could see in that circle? And that's what we're going to actually try and do right now. We're going to generate such a thing, which is a dispersion map. And we're going to generate it using a 200 arcsecond smoothing circle. In other words, we're going to take a circle of around 200 arcseconds in the sky when we look at it. And we're going to now find out within the circle, away from every point, what is the range of possible values of velocity for this star. So just as before, we're going to have to convert arc seconds to kiloparsecs. Remember earlier we converted degrees to kiloparsecs by just multiplying by 13.67. But of course, a degree has 3600 arc seconds. And so we need a way to convert. We just need to divide this number by 3600. And then we define two empty arrays here, which are two arrays of zeros. So you'll start off with a bunch of zeros. How many of them? As many as the length of the x coordinates. In other words, as many as there are stars in our galaxy, in this particular simulated galaxy. And I will also have another array here, which would have give you like values, I think, of sigma, of the standard deviation. And then I define a smoothing circle to be 200 times an arc second in kiloparsecs. So 200 arc seconds, that size in kiloparsecs. And then for every one of these different elements down here, for every one of the stars in our galaxy, I'm going to draw a little smooth. I'm going to take this little smoothing circle around, and I'm going to draw a circle around that point, and I'm going to find the dispersion about that point. So if some of you might be a little unsure about the idea of dispersion, but essentially what we're going to do is we're going to assume that all the velocities follow a sort of bell curve about that point, and we're going to see what the deviation, the standard deviation, in other words, the distance of these points away from the mean is. And now we're going to plot the graph with our disk, which is the simulated disk here, and the quantity that we defined in this disk here, which will change the color of each of these individual stars, is not going to be the velocity like we did in the previous notebook, but is instead going to be the list of sigmas, the standard deviations around this point. And so I'm going to run this cell right now, and you're going to get another disk very much like this, but the colors will look very different. So I'm going to run this, and you can see. Great. So you see that there's a disk over here. And with this disk, you see that there are associated colors around every point. And these colors represent the standard deviations. In other words, the variations of the velocities about that particular point. And this will give you the result. 1 second. I'm just going to make sure that I've not changed anything in this notebook. Right. So if all of you run this, you should be able to see this. And now you can change the size of the smoothing circle. You can make the smoothing circle very small, or you can make it very large, and you can see what exactly would happen. So here's a question to everybody. What would happen if instead of using a 200 arc second smoothing circle, I actually used a much smaller smoothing circle? Let's say a 20 arc second smoothing circle. What would you expect to happen in this case? So what are we doing here? We're choosing a much smaller range around the star, and we're trying to ask what would happen to the range of velocities within that region of space. Does anyone have any ideas? Let me run this. Oops. And what's important to see is that the colors are pretty similar, because actually what happens is when you're so close, there aren't that many stars around you. And so the deviation is not very large. And so all regions have roughly the same standard deviation. Similarly, you could do this for a much larger. So you could do, say, 3600. Maybe not 3600, but in, say, 500 seconds. And now you're choosing a much larger region. Okay, and so you're covering a much wider part of the galaxy. And again, you would see that these things get pretty homogeneous beyond a certain point, except around the center, which has the largest amount of velocity dispersion, because about the center, you have stars that are moving both towards you and away. So we're going to stick with 200 and just run this. There we go. And that gives us our little disk. And I think there are some
Philip, if I can just chime in for a brief moment. If you made the circle so big that you include the whole galaxy, then you'd get the blue shifted and red shifted sides. All stars would have the same neighbors. Yes. All stars would have the same dispersion value. That's an extreme where the circle is so big that it includes all stars.
What value could I use for that? Should I use something like, I don't know, 2000? No.
No, if you did, it would lose its diagnostic power
So it wouldn't
it
really
would
use.
no longer be a local measurement. It would become a global measurement. What we want is a local measurement.
So that would be what is the possible range that every star has? What's the average sort of dispersion that every star would have? But what we're more interested in is location by location, what is the dispersion? Is that right, Raja?
That's exactly right. We are interested in location by location. Now, mind you, what you plotted here is a cold disk with very little internal dispersion. And what we see in Andromeda is there's a lot of internal dispersion. That's why that's one of the parameters. Dispersion is a parameter for fake disk.
So we can put in a much higher dispersion, right? In principle, I could say.
You can put in fact, if you put in something that's comparable to the rotation speed, you'll see that the pattern will look a lot less systematic.
Okay, so let's put in a dispersion of around 200 because the rotation speed is 200. Now I rerun this. And you see, oh yeah, you can see that there are these little, I don't know if people can see it online, but you can see that there are little patches that seem to be forming all around the place.
Yeah. And Philip, one thing you might try is increase the number of data points from, you've got 10,000 now?
Yes, exactly.
Try to go to 50,000. It'll slow down things a little bit, but not significantly.
Should I increase the dispersion as well or leave it as it?
Yeah, with the dispersion you have, just increase the number. You'll see the patterns a little better.
Ah, there we go. Yeah, you can see a little bit these hotter and colder spots that appear here. This might take a little bit of time to run on your computers, but you can see these patterns.
In fact, the average color, that's the dispersion map. The average color will be around 200.
Yeah, and that seems to be about right.
And whereas in the other map, in the rotation map, you'll see a lot of scatter. In fact, if you make the dispersion 1000, we won't be able to see the rotation pattern at all.
Let me try that. Let's see.
Because you're dominated by disordered motion.
It just looks like static because at every point there's just a lot more dispersion.
You can still see a slight gradient from the top to the bottom, but it's very slight.
It's a little yellower here and a little bluer here. And if I now create this graph, let's see how long this takes to run. Yeah. It's a lot more smaller patches around here. And I suppose if I change the number, the region over which I was averaging, I would see different things. Yeah, right. See a lot more variation. Okay. Is there anything else I should do here, Raja? Should I move on to the velocity dispersion activity?
No, this is good. I think in Andromeda, we will find that the dispersion parameter, the velocity rotation parameter is about 250 or 200, and the dispersion is about 100.
Go back to that. Those were our original numbers. I'm going to set the number back to 10,000.
And what PA are you using? Is it 37?
Yes, 37.
And that's, again, designed to match Andromeda.
And the inclination as well. Great. Okay, so that's it for this particular notebook. There are a couple of questions down here that you can try and answer. But now let's move on to notebook number 6, which is the velocity dispersion activity. And now what we're going to do is combine the ideas from the different notebooks together and try and see what information we can get about the different classes of stars. So earlier we were talking about, when Lodrick started off, he spoke about how we can classify these different stars into these different 3 families in some sense. And when I started off, we were talking about how we can get the velocities of these stars. And now what we're going to try and see is look at the dispersion as a function of the type of stars. So just as before, we're going to start off by loading these different packages that we need. We don't need fake disk anymore because that was just there to get us a sense of how we would measure dispersion. So we're not going to take that in now. We're going to actually use actual data. And we're going to, again, have the same show map function that we had before. And this function also now saves the file, which I don't think it used to do in the previous file. But right now you can also send in a file name, and you could do a plt .savefig, which would save this as a file name in the same folder that you're currently in. So some people were asking about this in the Slack yesterday, and so this is how you do it. And now we're going to do what's probably like the most difficult function in in this tutorial. I think at least it's the most conceptually difficult function. So I'm going to undo the stuff that I've written here, and I'm going to start explaining step by step what I do. So before we start this, I'd like to just talk a little bit more about NumPy arrays for just a minute, because some of you might have forgotten what we did the start of the last session. So the beauty of NumPy arrays, especially for people who are doing physics or astronomy, is that they work very much like what we would call vectors. In other words, they do things that we would think of as common sense operations, and that makes a lot of our computations much faster. So for example, let's say that I define some array as being, say, the following array, which is 1, 2, 7, oh, 7. And let's say that what I want to do is subtract a certain number from every one of these objects. So what I could do normally is I could run a loop, which we've seen before, and we could go from element to element, take every one of these elements and subtract a number from it. But we can also do something else, which is very nice, which is we could just take the array and subtract a specific number from it. So for example, let's subtract the number 3 from it. And when I run this, it returns a NumPy array, but at every point I've taken what was 1 is now 1 minus 3, what was 2 is now 2 minus 3, and so on. And so I have been able to return an array of values where every element has had this number subtracted from it. And this can be very useful, and we're going to use this right now when we actually use the get dispersion function. So in order to use the get dispersion function, first of all, it takes in a couple of parameters. It takes in a set of x's, in other words, a set of x coordinates. It takes in a set of z coordinates. These are the coordinates of the different stars in Andromeda. It takes in a set of velocities, because it's the dispersion of the velocities that we're interested in. And then it takes a circle size. And this is the smoothing circle size that we were looking at earlier. This is the size of the circle within which we're interested in looking at the dispersion of velocities. And this is the default parameter. By default, the value is 300 by 3600, in other words. But we could change this value to some other value. So I start by defining for every one of these points, in other words, for as many zeros as there are stars, I define a value of dispersion, okay? And then I have to loop over every one of the stars. In other words, I have to loop over every point that has a specific x or z coordinate. And I do that using this for loop. So I go over an index I, which is in the range from 0 to the length of x in steps of 1. So we'll first start off. So I will take the values 0, 1, 2, 3, and so on. And then what I do is every one of these points is, of course, a star. And I take the x coordinate and the z coordinate of that particular star, and I store it in a variable that I call this x and this z. Note that, of course, what we're calling z is effectively like in an xy plane. If you're more comfortable, you could just call everything y here, and there wouldn't be a problem. But right now, this is defined in terms of x and z. And now what I have is a list. So I've given in a list of all the possible x and z coordinates of the star, and I'm looping over every single star. And now what I want to do is I want to find all stars that are a distance circle size away from us. So the circle size is sort of the radius of a circle within which I want to find every star. So the first thing to do is I want to calculate the array of all the distances of all the other stars away from this star, okay? And I do that in the following way. So I use the standard distance formula. What is the standard distance formula? If I have 2 points, x1 and x2, x1, x2, and x1, y1, and x2, y2, and I want to find the distance between them, then let me just write out the actual distance formula in a markdown code so that everyone's okay with this. Then the distance between these two is basically the distance d is equal to square root of x1 minus x2 the whole square plus y1 minus y2 the whole square, right? And so this is the distance from x1 minus the difference between the x coordinates and the y coordinates. I square them, I add them together and I find the square root. And this will give me the distance of between the stars x1, y1, and x2, y2. So I want to now do this for every single star. And the good thing about these NumPy arrays that I have up here is that it allows me to do that in essentially one line. So I do it in the following way. I take the array X, which is the X coordinates of all the stars, and I subtract from it this X. So this will give me an array of X coordinates of all the stars, how far away they are from this X, the particular star that I've chosen. I then square this. Notice that in order to square it, I have to put 2 stars. I square it. And then I add to this the distance of all the other stars, the difference of all the other stars' y coordinates from, z coordinates from this z. So I do a z minus this z square. And then I take a square root of all of this. And the square root can be done because NumPy has a very nice simple function called np.sqrt. And this would find the distance. So the dist here is an array of distances of every star in the galaxy away from star number I, the specific star that we're looking at. And now we don't want all of these stars. We want to only keep stars that are closer than a distance circle size to the star I. So in other words, we have the entire set of stars in Andromeda, but we want to restrict ourselves to those stars that are a distance circle size away from star number I. So we do this by creating a little Boolean mask. In other words, we create a Boolean array that returns true if a star is at a distance closer than circle size to this particular star, and false otherwise. So in order to do this, we just write out dist, which is this array of distances. Keep in mind that this is an array, okay? It's a list of many different elements. And I'm looking for all values where the distance is less than circle size. Okay, and what this is going to do is that it's going to return an array of trues and false. So for example, let's check over here what that does. Let's do a simple test. So this is my little NumPy array, and I want to return all values where array is less than 7. So how do I do that? So I do array less than 7. So what this is going to do is it's going to return a list of trues and falses. It's going to take the first element, say 1, and say, is 1 less than 7? Yes. So I'm going to return true. And it's going to do the same thing for 2. The minute it gets to 7, it's going to say, is 7 less than 7? No, it isn't. And so from 7 onwards, everything else is going to be false. And so we're going to see that exactly here. You see the first element was true, the second element was false, and all the others are, second element was true, and everything else is false. And if I had a number here, say the number 3, and I ran this, you'd see that there'd be an extra element at the end, which is true, because 3 is, in fact, less than 7. Now, if I wanted to pick out only those values of array that have a value less than 7, I could do it in the following way. I could say array of this. So I am now sending in, I create first a little Boolean array, in other words, an array of trues or falses, and I send it in and I call those elements of the array that happen to be true. And in this case, if I run this, it's going to give me 1, 2, and 3. And if you run it, there indeed, you see that it is in fact 1, 2, and 3. We have picked up those elements that are less than 7. We could also pick up those elements that are greater than or equal to, for example, 7, in exactly this way. So we send that in and we get all values that are 7, 10, 24, which are these values. So that's exactly what we're going to do here. We're going to get from here a list of Booleans, an array of Booleans that we're going to keep. And this is a mask. In some sense, it's masking out all the data that we're not interested in. And now I have gotten all the stars. So I know the stars I want. So I can define a little array, which is, say, stars I want, which happens to be, I don't like putting I in. So let's say, so valid or nearby stars. Let's define that. Nearby stars, which is just all all of the stars, the velocities, by stars V, which is the velocities where I've applied this Boolean mask keep. So this will return a list of velocities, an array of velocities that are only for those stars that happen to be less than circle size away from the star I in question. And so the dispersion of star I is now going to be the standard deviation of the nearby star's velocities. So in other words, I'm going to assume that there's a sort of bell curve of velocities around me. And I'm going to say, what is the standard deviation of this bell curve? That would be done. Again, the standard deviation, NumPy has an inbuilt function that can find this. So the function np.std function, NumPy.standard deviation. And I can find the standard deviation of this particular array. And all of this is done for star number 0, and then you go up to star number 1, and then you do it for star number 2, and so on. And you will end up with this dispersion array, which was initially filled with zeros, but by the end is no longer filled with zeros. And this is what's going to be returned to us. So if I run this now, there aren't any errors. Of course, nothing's happened because we've just defined the function. But now what we're going to do is we're going to actually load these catalogs that we created at the end of notebook 3. So all of you should hopefully have them. And once we create this catalog, we're going to load all of the data in the catalog. But since we know that the only data that we're interested in are the xi and eta coordinates and the velocities, we're just going to use some specific columns, and that can be set using the useCalls parameter of the load text function. And so I can take in all of these parameters, and then I can store them in 3 different variables, xi, eta, and v. Now, these lines are very important. They're to take account for a bug in the catalogs, which essentially, if I've understood it right, means that if the velocities, the absolute velocity, the magnitude of the velocities of these stars is greater than 1,000, then chances are they aren't actually part of this galaxy. So they were chosen sort of accidentally. And so this just cleans up the code a little bit. So we're going to keep it whenever we use this code. So this is very important. So don't remove these lines. And now since I've loaded the catalog by show map, just like I did before, and it's going to plot, instead of the color, it's going to give us the main sequence dispersion. So in other words, what I've done here is I've loaded a catalog of those stars that we have chosen to be main sequence stars. I'm doing a show map.
Philip, I think you cut out for a moment there.
I'm so
Right after explaining the debugging block of code.
I see. Okay, that's this particular block of code, right?
Yeah.
I see. Sorry about that. I think my internet isn't particularly stable. So, once we've got our catalog and we've cleaned it up, then what we do is we try and get the dispersion of this catalog. In other words, we take the xi and eta, which are the x and z coordinates, and the velocities for every star, and then we plug it into this get dispersion function that I've just described above. And this will give us a list of the dispersion for every main sequence star. So we've created these main sequence stars, the catalog of these stars earlier. And then for every one of these main sequence stars, we find the dispersion about it. And then we're going to show a map just as before, but with only the main sequence stars xi and eta, and the color representing their dispersion, just like we did in the fake disk activity. And then over here, I'm going to save it to this particular location, which is in plots folder, an MS dispersion map. Okay. So I'm going to run this. And here we go. So you'll notice that there are much fewer stars here than we saw in the radial velocity activity. But that's because we've actually only restricted ourselves to the main sequence stars in Andromeda. And that we've done that by only loading the main sequence catalog up here. And so that's what shows you the dispersion over here for the main sequence stars. And you can see that there are, of course, specific different colors here. So you can see that this region is a little greener, this region is a little more violet. So the dispersion is around 40 mostly in this region, but over here it can go as high as 160. So now what the exercise that you guys should do, and I hope you all managed to do this, I'm going to do it in front of you as well, is to fill in the same code that we've done over here. But instead of main sequence stars, we're going to do it for both the AGB as well as the RGB stars. And it's going to be very simple because it's very similar to the main sequence. So I'm just going to copy this entire cell and I'm going to paste it down here. And I'm going to make some changes. So the first change is that instead of using the MS catalog, I should load the AGB catalog. I need to keep the section here as well because the same bug exists. And then I'm going to name this function, instead of naming it MS sigma, I'm going to name it AGB sigma. And then when I plot the color map, I want the AGB sigma here. And I want to name the plot AGB dispersion map. So I hope I have the AGB catalogs, otherwise we're going to be in trouble. But I'm going to run this. Oops, I don't have the AGB catalogs. Oh dear. Just give me a second. I'm just going to copy that in. And hopefully this shouldn't be a problem. Just a second.
And normally the AGB catalog gets generated by notebook 3. But, you know, Philip, you may have run it at some other time in a different directory. But yeah, copying it over will solve the problem.
Just give me a second. I have it here. I just need to copy it into this directory. That's all I have to do. Just once. In the meantime, you guys can try this out with the other catalogs.
Yes. If you are following along, you should have the two, you should have all 3 catalogs, MS, AGB, and RGB.
There we go. So now this is my AGB dispersion, and you can compare it to the MS dispersion. So this was the main sequence dispersion, the dispersion of real data, as opposed to the fake disk from earlier. And down here, we have the AGB dispersion of data. And you can see that it does seem to occupy a much larger region of the galaxy. But of course, there are many gaps in between them. And now we're going to do exactly the same thing, but for the RGB catalog. So again, I copy the previous cell and I paste it down underneath here. Oops, of this. Just as before, I'm going to change the AGB to an RGB here. And then I'm going to change the name here to RGB and the name here to RGB and the dispersion to RGB. And when I run all of this, I get the red giant branch. And you can see that these are, of course, this seems at least to be the largest number of points that we have so far. So you can compare them. And you can see that there's a lot more. So the overall range of dispersion seems roughly the same, but you can see that there are many more stars in the RGB branch here in Andromeda. And that you should also remember from the graph that Lodrick showed you, where you had this huge concentration of stars at one point, which happened to be the red giant branch.
And so that was in the lower right part of the color magnitude diagram, the things that were colored red. Now, I just want to comment on the color of this. I see a lot of greens. I don't see a lot of dark colors here. I don't see a lot of blues or dark blues. I see greens, light greens, even some yellows. Overall, the average colors are higher up on this color bar compared to even AGB stars, which tend to be a little bit of a darker shade of green. You see some greens and blues. There are fewer points, it's hard to tell. And then you contrast that with main sequence, which really tends to be much darker colors.
Exactly. So, Raja, would you like me to do the histograms now, or would you, because
we're
running,
sure.
No, we're running out of time. Do you need to give a little bit of...
I have time. I'll take 5 minutes for that. You go through the histogram. I think after you do the histogram, that shouldn't take time. Let's come back to that key line in the notebook where you set up the the keep, the Boolean array, all of that. That was such an important line. That's probably the most complicated line of code in all of our 6 notebooks. I would just like to do the histogram, just come back to that, then I'll do the fact.
So now what we're going to do is actually very, very simple. What we're going to do is just put in a histogram of of each of these different things, which is of the main sequence sigmas. We're going to basically plot the range of, say, main sequence sigma. So I'm going to copy a line of code here, and I'm going to paste it in. It's because it's faster to copy than to write it out. And I define an axis just as before, and I'm going to plot a histogram of the main sequence sigma, the variable that I stored above. I'm going to define a bunch of bins. So how many different values am I binning these things by? And I'm going to run this. Oops, what has not worked? Just a second. Oh, this is, just a second. I don't know what normed equals 1. So I think this might be an older code that I was using. Yeah, okay. I think that's used to be called density. I think it should be density. That's true. It is.
Yeah, this part of this code is deprecated.
Yeah, so this is an older version of the code. But yes, okay. So you see that there is a histogram here, and I can put the edge color as just black. And there we go. So now we have a histogram, and this tells us for the main sequence stars, and I can put in actually a label that says MS, for example, and print the label out. And this tells us that for the main sequence stars, this is the distribution of dispersions. And you can see that the distribution is around something around maybe 60 or so. And that was, of course, the lower end of the color bar. And that's why you can see that in the main sequence graph down up here, you can see that the velocity dispersion is in fact closer to this. You can look at the colors here. You can see that it's actually closer to the lower end of the color bar. In other words, these stars are not particularly dispersed. So in other words, they're sort of behaving similarly to each other. They're traveling similarly to each other. There's not that much dispersion. Now I can repeat exactly the same thing, but I can do it for the RGB stars. And now you should be able to know what I should change. I should change this to RGB. Let me change the color for RGB to be red. Let's put an R here. And I'll change the label to be RGB. And everything else I think should be same, except, yeah, that's good. And then when I run this now, I see that we have the RGB stars. And you can already see that between the main sequence and the red giant branch, both these histograms are quite distinct from each other, and the RGB is more pushed more towards the right. So let me actually put in the axes, because without the axes, none of this makes sense. So I'm just going to put in some axes down here. There we go. So the x-axis are the sigmas, in other words, the dispersions. The y-axis are the normalized counts, in other words, just the relative ratios of each of these stars. And you can see that the main sequence stars are have a much lower dispersion than the red giant branch, which have a much higher dispersion, and there's almost no overlap between them. And now I can do the same thing, but for the AGB stars, I'm going to make it green, because that was, I think, the color that we used in the CMD, the color magnitude diagram. And to make this G, and the title, the label AGB. And when I run this, you see that the AGB stars is sort of in between this. They have a much larger overall, like the possible range of possible dispersions is also quite large here, but it sits sort of in between both of these. And so this allows you to see the different histograms, and it allows you to plot data and actually extract more information from the data that you wouldn't normally have just been able to get from this. By looking at this graph, you should be able to know, as Raja pointed out, that it's greener and there's more greens and yellows, while the main sequence stars has more blues or violets. But this is a mathematical way to actually get it, to actually plot this histogram out. And this will tell us that one of them has a much lower dispersion and the other has a higher dispersion. So, and you can also plot out the median values, for example, by using the np.median function. And you could do so, for example, print main sequence median values as being np.median of main sequence sigma. And if I print that, it tells us that the main sequence median values are around 60, which is sort of what we saw. And we can now do it for RGB median values. And we should expect that this be a much higher value. And when we run this, we see that it's around 105, which is in fact the case. And down here, I can do the same thing for AGB median values. And that gives us a value that's very close to around 90 to 100, which is what we see over here. Okay, great.
This
So
confirms our visual impression of the map that the RGB stars are the hottest. The AGB stars are only slightly different, not as hot, but the main sequence is really significantly lower.
exactly. Okay, I think I'm done with the notebook.
Do you want to go back just for a moment to that line of code, the key line of code? Again, we don't need to dwell on this line of code, but I just want to say that those, maybe not just the one line of code, but even those three lines of code, dist equals how you calculate the distance and how that goes into an array, the keep array, and how we define nearby stars. They're very compact. There are three very short lines of code. One of them has the Pythagoras theorem in it. The first of those, that's a distance calculation. But it is this compactness, the elegance and simplicity, apparent simplicity of the code that's doing something very complex that makes it challenging. This is actually what makes it, this is in mathematics, in coding, things that look simple but are actually doing complicated things are the most difficult things to deal with. And I just wanted to highlight these three lines of code. If you take nothing else away from this notebook, remember that those three lines of code are the most complicated section of the entire 6-notebook tutorial. Just wanted to say that. All right, I have my slides ready to go. I'm happy to share my screen, and I'll just share my whole screen for now.
And Raja, a quick addendum. When you say AGB and RGB are hotter than main sequence on that, on those plots, you mean dynamically hotter, right?
Hotter. They have a bigger spread of velocities. They're not temperature hot.
Yeah, this is not surface temperature.
By analogy with the speed of molecules in a gas, so dynamically when a set of molecules in a gas is hot, when the gas is hotter, the molecules are moving more rapidly with more random motion. So it's, I was using an analogy for a dynamically hot versus dynamic. That's a very good point. I can't share my screen. I would need, I'll need co-host permission.
Let me see if I can make you co-host.
Sorry, thank you. I can do it now. Sorry about that. I didn't log in with the correct permissions. My fault. All right. Give me 1 second. I'll start my screen share. And so this is very quick. I know we're nearly at the end of our time, but some of you know this is my favorite galaxy in the whole world, Andromeda. That's the main ellipse you see here across the middle. This is a photo taken by Robert Gendler. This is not its true orientation in the sky. Its true orientation in the sky relative to north and east is not like this. It's like the notebooks, like it was in the notebooks. But I want to point out that next to Andromeda are two companion galaxies. If you can see my cursor, one of the companion galaxies is down here. Let me see if I can get a different, okay. You can see my, hopefully you can see the arrow, that's my cursor. So this is M32 and this is NGC 205. And we study these galaxies with the Hubble Space Telescope, but also with the Keck telescopes on Mauna Kea. And the Keck telescopes are coming into view right here gradually. It's a beautiful Mauna Kea sunset photographed by Laurie Hatch. And if I go to my next slide, here you can see why we were looking at a lopsided portion of the Andromeda ellipse in all our earlier maps. This sort of white outline, what looks like a crime scene outline, is what Hubble covered of Andromeda, the Hubble Space Telescope covered of Andromeda. Over 4 years, in 828 orbits of the Hubble telescope around the Earth, each orbit lasting 90 minutes. These 828 orbits were distributed over 4 years. There were measurements made in 6 filters, 2 in the ultraviolet, 2 in visible light, 2 in the near infrared. It's a project led by Julianne Del Canton. She was then at the University of Washington. She's now at the Flatiron Institute in New York. But our UCSC-based team did a lot of the spectroscopy with Keck and Deimos using the telescopes you saw on the previous slide. And again, if you plot individual stars at dots and they're within this rectangle, within this outline, you're going to see a portion of an ellipse. You don't see the whole ellipse naturally. Okay. Now what we're going to do is we're going to zoom in so you can see some of the details of the Hubble image of Andromeda, and I'm keeping track of time, so I won't take much more than another minute or two. But this is the arc of the Milky Way that you see going across, and here's Andromeda, 2.5 million light years away, as this tiny little ellipse that you can see my cursor on. So I'm going to remove the label so that we can see the details of this galaxy as we zoom in. Again, we're going to zoom into this galaxy that's 2.5 million light years away. As we zoom in, you'll see its companions. Here's one companion. Here's another. You can see those two companions, but we're going to keep zooming in until you can see even more detail in the Andromeda galaxy, until you can see individual stars that you can see now in the Andromeda galaxy. Individual stars, some as hot as the sun, some much hotter than that. The really hot ones look blue in this picture, and some much cooler, and those look red or orange in this picture. Sun-like stars, temperature-wise, sun-like stars look yellowish in this picture. So we've had the privilege of studying 117 million stars with Hubble in the Andromeda galaxy, and about 10,000 of them we've taken spectra of them. And this is an example of patterns that we used last fall, 2023, and in 2022 fall. This is using a particular instrument on the Keck telescope, and what results is a map like this. And now you can see more of the ellipse, because what Philip and Aparajita were showing was the upper part of this ellipse, just this part up here. And now this part was filled in a few years ago, and over the last couple of seasons, we filled this in. We avoid the central part of Andromeda, which is there, because the stars, things are too crowded. The stars are too close together to get meaningful measurements. Okay, every dot again is a star in Andromeda, and its color denotes its velocity. Now you'll notice that the colors are different over here, and that's because there's another galaxy, that's M32, that's moving at a different speed than the disk of Andromeda. All right, I'll stop there. I'll stop sharing my screen, and let's we're back to seeing the participants who've remained. And thank you so much to all the mentors, Lodrick, Doug, who's not here today, Aparajito, Philip. I know Antara was, had other obligations, but I don't know if she was able to contribute on Slack, Zoom, but I know she's been a big player in this. I also wanted to thank Maddie, because it's her slides that did a beautiful job of explaining what we understand about stars and how we measure their properties.